Have you ever thought about what would happen if we could trap the sun? Not destroy it, not dim it, but actually build something around it. A gigantic structure that could capture every bit of its energy. It sounds insane, right? But here's the thing. It's a real scientific idea. And if a civilization could actually pull it off, it would have power beyond anything we can imagine. It wouldn't just change life on Earth. It would change what it means to be a civilization at all. This idea, a machine built around a star, is called a Dyson sphere. It's the ultimate step in energy evolution, and it starts with something as simple and ancient as our relationship with the sun. Long before we dreamed of space travel or fusion, we were already building our lives around a star. We just didn't know it yet. We don't often think about it, but the sun is the reason we're here. Every plant, every animal, every breath of oxygen, all of it exists because of sunlight. And for most of human history, people didn't just see the sun as a source of light. They saw it as a god. In Egypt, it was Ra, creator of all. In Greece, Helios drove his golden chariot across the sky. To the Aztecs, the sun demanded sacrifice. Even in early China, legend spoke of archers shooting down excess suns that once scorched the earth. In every culture, the sun was life itself, something to fear, respect, and depend on. People tracked its path across the sky, marking solstices and seasons with monuments that still stand. They didn't understand the physics, but they understood the rhythm, the heartbeat of the planet pulsing in step with the sun. Over time, those rituals evolved into measurements and mathematics. The sun became more than a symbol. It became a tool. As civilizations advanced, humans learned to capture and control energy. We burned wood, then coal, then oil. Each step gave us more power, but also more limits. Fire cooked our food. Coal built our cities. Oil fueled our machines. And now, electricity runs through our lives like blood. Yet every energy source we use still comes, in some way, from the sun. Fossil fuels are ancient sunlight stored in plants and animals. Wind is air moved by uneven solar heating. Even solar panels only skim the surface of what the sun gives us every day. Earth receives about 173,000 terawatts of solar energy continuously, 10,000 times more than humanity uses right now, and we capture only a fraction of it. The sun wastes more energy in a single second than we've used in all of human history. So the question becomes, if all our power comes from the sun anyway, why not go straight to the source? Why not capture everything it gives off? That's what led one scientist to propose something extraordinary. In 1960, physicist Freeman Dyson published a paper barely 3 pages long. But those 3 pages changed how we think about civilization forever. Dyson's idea was simple. If a species keeps advancing, its energy needs will keep growing. Eventually, it will exhaust the energy of its home planet. So what would it do? It would build something around its star. Not a solid shell, but a swarm of orbiting collectors, each capturing a fraction of its light. Together, they'd form a vast network, a cosmic net absorbing most of the star's energy. Dyson wasn't imagining humans in particular. He was asking a broader question. If we ever searched for intelligent life, shouldn't we look for stars whose light was partially blocked or re-radiated by such structures? A Dyson sphere, if it existed, could reveal itself through its strange glow. Dim, invisible light, but bright in infrared. His paper wasn't about fantasy. It was about evidence. And even though science fiction later turned the idea into legend, Dyson's concept became a symbol of ultimate mastery, not over others, but over nature itself. 4 years later, another scientist, Nikolai Kardashev, introduced a way to measure such progress. His Kardashev scale ranked civilizations by their energy use. Type 1 could harness all energy from its home planet. Type 2 could harness all energy from its star. Type 3 could command the power of an entire galaxy. Humanity? We're about 0.7, still struggling to use our own planet efficiently. But building a Dyson sphere, or even a Dyson swarm, would push us into Type 2. It's not fantasy, it's a logical step forward. When you imagine a Dyson sphere, don't picture a solid shell of metal that would collapse under gravity and heat. Instead, think of billions of satellites orbiting in sync, forming a glittering halo around the sun. Each would gather sunlight and beam it back to a central hub using microwaves or lasers. It wouldn't block the sun completely. To distant observers, it would just look dimmer, its color shifted by the waste heat of all those machines. And if astronomers ever detect such a signature, it might be our first proof of another advanced civilization. But even if no one's built one yet, the idea changes how we think about ourselves. It asks, why do we care about capturing a star's energy when we can't yet manage our own? Because ideas like this remind us what we could be. They force us to look at the sky differently. The sun stops being just a light. It becomes a challenge. The universe runs on energy, and whoever masters it shapes their destiny. Every spark in our history, every fire, every reactor, every solar panel is a step along the same path, learning to control light. Fire is fusion, slowed down. The sun is fire, perfected. We've always been trying to reach it, to match its power in our own hands. A Dyson sphere is just the farthest, most daring end of that pursuit. Right now, we capture less than 1/billionth of the sun's output. The rest streams into space, untouched. To a Type 2 civilization, that's unthinkable. Like letting oceans of power slip through your fingers. For them, building around a star wouldn't be greed. It would be survival. Stars die. Planets perish. If you want to outlive your world, you need to master your star before it fades. That's not ambition. That's inevitability. We might be thousands of years from even beginning such a project. But the point isn't prediction. It's perspective. The Dyson sphere isn't about machinery. It's about mindset. It's about seeing the sun, not as a limit, but as a beginning. If you step outside on a clear morning and feel the warmth on your skin, remember, that light left the sun 8 minutes ago. It traveled 150 million kilometers through the void just to reach you. Every second, trillions of photons pass through you. The same energy that grows forests, fuels storms, and powers life itself. All of it from one star. The same star that could one day become our engine, our shelter, our bridge to the cosmos. Maybe that's our destiny, not to escape the sun, but to understand it deeply enough to live with it completely, to build around it, thrive from it, and share its light across the stars. Because the story of the Dyson sphere isn't really about technology. It's about curiosity. The same question humanity has always asked when we look up. How far can we go? In the stillness of ancient nights, our ancestors gathered around a simple fire, spellbound by its glow. They huddled close as sparks from the burning wood spiraled upward, joining the tapestry of stars in the sky. That first flame was more than warmth or light. It was a tame piece of the sun, captured on Earth in a dancing ribbon of orange and gold. For the first time, humankind held dominion over a small slice of nature's power. It was as if, like Prometheus in legend, we had stolen fire from the gods. The crackling campfire kept the darkness at bay, and its dangers with it, allowing our stories and dreams to dance in the nocturnal air. As centuries passed, we learned to harness the breezes and currents that flowed across the land and sea. Sails billowed and carried us across oceans with the invisible push of air. On land, windmills turned under open skies, grinding grain with the breeze, while water wheels captured the steady rush of rivers. Yet these gentle forces were only a prelude to a far greater bounty hidden in the earth itself. With the spark of the Industrial Revolution, humanity fed wood and then coal into hungry furnaces, releasing energy long stored away. Steam engines powered by coal drove iron wheels across continents, and steamships churned across the seas, knitting far corners of the world together at newfound speed. Soon, black coal and slick oil, ancient sunlight trapped beneath rock, became the twin fuels of progress, feeding the machines of industry and forging an era of growth. Oil wells yielded liquid light from the depths of the earth, fueling lamps and early engines that carried people and goods farther and faster. By night, whole cities glowed with man-made brilliance as the energy of bygone epochs was unleashed to banish darkness. In factories and on railroads, the might of steam and coal was reshaping landscapes and lives. With each step forward, the energy we harnessed transformed how we lived and what we could achieve. When wood gave way to coal and oil, villages blossomed into industrial cities powered by steam and light. Electric grids wove a humming network that bound communities together and pushed back the ancient darkness. Energy had become the lifeblood of civilization, and as that lifeblood flowed ever stronger, human ambitions grew with it. By the dawn of the 20th century, each person in an industrial city could call upon more energy in a day than whole villages did in ages past. Life was irrevocably changed. What once was done by muscle and wind was now accomplished by the concentrated fire of fossil fuels. Each new source of power brought more energy under our command. In the 20th century, we discovered fire's ultimate heir, the energy locked inside the atom. Splitting uranium released a ferocious heat, turning tiny quantities of matter into bursts of power beyond any furnace or engine. Nuclear fission lit lamps and powered ships. Its reactors hummed with a contained inferno, a testament to our growing mastery of nature's hidden forces. It was as though we had learned to bottle lightning, wielding a force once thought to belong only to the heavens. We had tapped into the very heart of matter, conjuring the sort of power that lights the stars. Even as we mastered fission, our eyes turned upward to an even more profound source. In the heart of every star, a different kind of fire blazes, nuclear fusion, where atoms join and new light is born. Scientists sought to recreate that stellar furnace here on Earth, dreaming of reactors where hydrogen could fuse as in our sun's core. In laboratories, magnetic fields held superheated gas in invisible cages, coaxing atoms to unite and release their brilliant energy. This quest for fusion was a reach toward the heavens, an attempt to bring a star's heart down to our own world. To spark on Earth the very process that makes the sun shine was a bold attempt to grasp the power of the heavens with human hands. With each discovery, our appetite for energy grew and our imagination stretched further. We began to ask what might lie beyond the fires we kindled on Earth, beyond coal and uranium, beyond even a captive starfire in the laboratory. If a single flame and then a single atom could be harnessed, what about an entire star? Even the sunlight we caught with mirrors and panels on Earth was only a meager sip from an ocean of radiance, a faint preview of what might be gathered at the source. The sun that rises every day pours more energy into the void than our world has ever consumed. To capture even a fraction of that stellar outpouring became the next grand vision, shimmering on the edge of possibility. Suddenly the idea of seizing the very engine of creation, our sun itself, did not seem pure fantasy, but an ambition glimmering just beyond our horizon. Fables like that of Prometheus told of stealing fire from the gods. In 1960, a physicist named Freeman Dyson pondered whether a civilization could steal the fire of an entire star and not be burned. It was a bold thought experiment born at the dawn of the space age, when the world below was only taking its first small steps beyond Earth. While rockets thundered into orbit for the very first time, Dyson's mind leaped light years ahead, picturing colossal works orbiting alien suns. In the quiet of his thoughts, perhaps gazing up at the night sky, he dared to ask a fantastical question. What if an advanced civilization could build a structure around a star to capture its energy? Dyson envisioned a society so advanced that its hunger for energy outgrew any planet. Such a civilization, he reasoned, would inevitably seek to harvest nearly all the power of its home star. Instead of letting precious sunlight spill uselessly into space, they would construct countless machines or habitats in orbit, each soaking up the star's radiance. Together, these orbiting collectors would form a shell of sorts, almost like a second skin around the star, capturing energy on a staggering scale. At the time, humanity's achievements in space were modest, just a few satellites circling the Earth. Yet here was a vision of engineering on a truly stellar scale. In Dyson's view, this was not just science fiction whimsy, but a logical next step in cosmic evolution. If life's survival and growth depend on energy, then an intelligent species would keep reaching for more. After mastering the resources of its home world, where else could such beings turn but their sun? Encircling a star with technology would tap into an almost limitless well of power, the ultimate triumph over scarcity. It would be a way to ensure survival and prosperity on a level previously unimagined, a kind of immortality for a civilization through energy abundance. That year, Dyson published a brief paper laying out this audacious idea in scientific terms. He suggested that astronomers could search the cosmos for the infrared glow of these distant star shells. If an alien civilization had wrapped its sun in a blanket of satellites, much of the star's light would be absorbed and re-emitted as heat. From Earth, we might detect that telltale warmth, a faint, distinctive whisper in the darkness, evidence that we are not alone. It was a revolutionary suggestion, to look for aliens not by radio signals or telescopes alone, but by the heat signature of their colossal works. This concept would come to be known as the Dyson sphere, forever linking Freeman Dyson's name with the dream of star-spanning engineering. Yet Dyson himself acknowledged that the seed of the idea was planted by someone else, a science fiction writer from decades earlier. He had been inspired by a passage in a 1937 novel where entire solar systems were surrounded by a gauze of light traps to collect escaping solar energy for intelligent use. What had begun as a novelist's fancy, Dyson transformed into a plausible cosmic blueprint. It was a shining example of how imagination and science feed one another. Fiction inspiring reality, and reality giving new fuel to fiction. For all its imagination, Dyson's proposal was grounded in real physics and a keen sense of cosmic possibility. It blurred the line between science and story, showing that the wildest ideas might just have scientific merit. Dyson himself never insisted anyone should start building such a sphere. He offered it as a thought experiment, almost playfully, to expand our thinking. In later years, he even mused that it ought to be called a Stapledon sphere, after the novelist Olaf Stapledon, modestly downplaying his own role in popularizing the idea. He didn't want credit, so much as he wanted people to stretch their imaginations to to match the enormity of the universe. Despite how it was later depicted in books and movies, Dyson wasn't picturing a single giant metal shell encapsulating a sun. He knew such a solid sphere would be mechanically impossible, given any material we know. Instead, he imagined a loose flock of millions upon millions of solar collectors orbiting in unison. A swarm, rather than a monolithic shell. Each piece would catch a share of the star's light, and together they'd form a nearly complete sphere from afar, shimmering with captured sunlight. The popular image of a vast hollow ball was, in Dyson's mind, more a convenient metaphor than an actual blueprint. The idea landed softly at first, a pebble dropped in the vast pond of astrophysics, but its ripples spread wide. It gave scientists and dreamers a new way to think about life in the universe, not just as biological beings on a single planet, but as builders and shapers on a stellar scale. Dyson's thought experiment became a beacon in discussions of extraterrestrial intelligence, guiding astronomers to broaden their searches and their imaginations. If such colossal projects were conceivable, what did that say about the potential of advanced life in the cosmos? The very notion urged us to think bigger, to imagine civilizations far older and more capable than ours, remaking entire solar systems to suit their needs. In the wake of Dyson's cosmic thought experiment, others began to ponder how to classify civilizations by their command of energy. It was becoming clear that harnessing a star's output would mark a new rung on the ladder of progress for any society. Before long, a Soviet astronomer named Nikolai Kardashev would propose a formal scale for technological civilizations, with Dyson's star-encompassing idea illuminating what a Type II civilization might look like. The conversation about life among the stars was about to grow even more grandiose and visionary, moving from single megastructures to the very categorization of cosmic societies. In the mid-1960s, inspired by ideas like Dyson's, Nikolai Kardashev proposed a bold way to chart the progress of civilizations. He imagined measuring societies by the energy they could harness, defining cosmic milestones of technological advancement. In Kardashev's scale, a Type I civilization taps into all the power available on its home planet. A Type II directly harnesses the energy of its star, and a Type III captures the energy of an entire galaxy. This simple yet sweeping classification gave scientists and futurists a new language for discussing the heights that intelligent life might reach. At Type I, a civilization can draw on every ounce of energy available on its planet. It could capture the sunlight falling on its world, harness the winds and the tides, and take power from every river and waterfall. Nothing would be left unused. Weather might be controlled and seasons managed, as the entire planet's energy flows are put to intelligent use. Reaching Type I would mean a society has become master of its homeworld, using power as freely as breathing air. It is a level often imagined as a kind of golden threshold, planetary unity through energy abundance. Type II marks an even more astonishing leap: the ability to harness the energy of an entire star. This is the realm of the Dyson sphere, where a civilization can capture the billions upon billions of watts pouring out of its sun. Imagine not just one world basking in starlight, but swarms of machines or habitats orbiting a star and drinking in its light completely. To achieve Type II would be to wield power on a scale that to us is nearly godlike. Enough energy to illuminate countless worlds, or to drive engines beyond comprehension. It represents engineering prowess taken to the stellar level, a feat of truly celestial ambition. Beyond even that lies Type III, a civilization that commands the energy of a whole galaxy. Such beings would harvest the light of billions of stars, tapping the power of supernovae and even black holes, channeling energies that span the breadth of a galaxy. To us, a Type 3 civilization is almost unfathomable, like magic performed on a cosmic stage. If Type 2 is godlike, then a Type 3 might seem akin to a galactic deity, reshaping entire star systems as effortlessly as we light a single lamp. This would be a civilization of almost unimaginable might and knowledge, the masters of a million suns. Kardashev's original scale stopped at 3. But later, thinkers have speculated about still greater heights. Type 4, even Type 5. Civilizations that could harness power on the scale of galaxy clusters or the entire universe. Those ideas verge on the mythical, stretching our imagination to its limit. What we know for certain is that humanity is still somewhere below Type 1, not yet having mastered even a single planet's full energy output. By some calculations, we are roughly a Type 0.7 civilization today, a fraction of the way up the scale. The scale reminds us of the immense potential ahead. It frames the Dyson sphere as a key milestone on the road to cosmic maturity, a stepping stone between our present and the farthest reaches of the scale of life. As scientists contemplated such staggering possibilities, the rest of humanity did not remain unmoved. These ideas of star-sized engineering and cosmic scales seeped into our collective imagination, blossoming in fiction and art. Writers, artists, and filmmakers began to play with the concept of Dyson spheres and star-spanning civilizations, translating cold equations and cosmic measurements into warm, vivid stories. In their hands, the dream of capturing a sun's light became something more human, a source of wonder, of caution, and of inspiration. Long before scientists had formalized these concepts, storytellers had already ventured into the realm of star-spanning civilizations. In 1937, British author Olaf Stapledon published the visionary novel Star Maker, which described cosmic beings reshaping entire galaxies and engineering stars. In one striking passage, he imagined every solar system surrounded by a gauze of light traps, each trapping the escaping energy of its sun for intelligent use. This poetic image, a star wrapped in a delicate web of light, was a spark of inspiration that would, decades later, echo in Dyson's scientific proposal. Through Stapledon's fiction, the seed of the Dyson sphere idea was planted in the fertile soil of human imagination long before the term existed. By the 1960s and 70s, science fiction eagerly embraced the Dyson sphere concept and its variations. In Bob Shaw's Orbitsville, for example, humans stumble upon a deserted sphere as big as Earth's orbit, a mysterious megastructure left behind by an alien super-civilization. Larry Niven's Ringworld reimagined the idea as a single colossal ring encircling a star. Not a complete sphere, but a habitable band of land curving around the sun in an endless loop. These tales brought the Dyson concept out of theoretical papers and into the minds of readers, making it a familiar marvel in the landscape of imagined futures. With time, the Dyson sphere became a familiar icon of the far future in popular culture. It even made its way to television. In the early 1990s, an episode of Star Trek, The Next Generation, portrayed an immense Dyson sphere discovered by astonished spacefarers. For many in the audience, this was the first visual encounter with the concept, a colossal artificial world with a star shining at its center. The idea was no longer a niche theory. It had entered the public consciousness as the hallmark of an almost inconceivably advanced civilization. Millions of viewers could suddenly picture a Dyson sphere, its vast interior landscape and central sun in vivid detail. Artists and illustrators also embraced the challenge of depicting a Dyson sphere. They painted scenes of impossible scale, continents and oceans curving upward at the edges of a vast shell, and an artificial sun suspended in the center, like a lantern in a cathedral. One can imagine standing on the inside of such a sphere, looking up to see not a blue sky, but the ground itself, rising above in the distance, an entire world wrapped around to form your heavens. The sheer strangeness and majesty of that image, a sky replaced by sprawling landscapes lit from a central sun, captures the profound sense of wonder the Dyson sphere idea evokes. It confronts us with a scenario at once awe-inspiring and disorienting, pushing our understanding of what sky and ground even mean. In fiction, the Dyson sphere became a canvas for exploring grand themes. Some stories cast it as a utopia, an Eden of endless space and unlimited energy, where want and hunger are banished by technology's triumph. Other tales turned it into a cautionary monument, a gigantic tomb, or a cosmic shell left behind by beings who dared to wield the power of suns and perhaps paid a cosmic price. In every case, the concept magnified human dreams and fears onto a cosmic stage. It invited us to ponder what incredible feats and follies a super civilization might achieve, and what destiny might await those who reach so far. Through imaginative narratives, the Dyson sphere became a mirror for our own hopes and anxieties writ large across the stars. Through these collective dreams made of light and star steel, humanity began to mentally grapple with the Dyson sphere long before anyone could build one. Imagination paved the way, turning an almost unthinkable engineering project into a familiar idea that we could discuss, depict, and even emotionally feel. By the time scientists and engineers circled back to ask the practical questions, the concept had already lived for decades in our stories and visions, growing richer and more nuanced. The stage was set for a shift in focus, from simply picturing Dyson spheres in theory to seriously wondering how, someday, one might be constructed in reality. The leap from dreaming to doing began quietly. In the late 20th century, a few scientists and engineers who had grown up enthralled by tales of Dyson spheres began to ask a very concrete question. What would it take to build one? They moved the idea from the pages of science fiction into the realm of engineering, breaking the grand fantasy down into daunting but tangible problems. The question was no longer just hypothetical or philosophical. It had become technical. How, in practical terms, might one construct a megastructure around a star? What technologies, resources, and timeframes would such an undertaking demand? Early discussions about Dyson sphere feasibility often sounded like something between a physics lecture and a futurist's daydream. Plans were sketched for swarms of solar collectors gradually multiplying in space, like a growing shell of fireflies around a flame. Some proposed using the raw material of an entire small planet. For instance, mining Mercury down to its rocky core, to supply the unimaginable quantities of metal and silicon needed for millions of orbiting panels. Others talked of deploying legions of self-replicating robots, machines that could build copies of themselves and construct pieces of the sphere in an exponential assembly line, slowly encircling the sun with a thickening cloud of energy collectors. Bit by bit, a vague dream was being translated into engineering schematics. Every approach acknowledged the titanic scale of the challenge, the number of structures required, the energy needed to forge and launch them, the precision to keep them all in stable orbits. All of it staggered the imagination. Even the thinnest Dyson swarm would involve millions upon millions of satellites working in concert around a star. It was clear that such a project could not be accomplished in a single human lifetime, or even in many lifetimes. This would be the work of centuries, perhaps millennia. It required thinking on timescales that dwarf entire eras of human history, plans that might be initiated by one generation and only completed by descendants hundreds of years hence. Yet, importantly, nothing in the laws of physics outright forbade it. The challenge was overwhelmingly vast, but it lay within the realm of the possible, given enough time and resourcefulness. Bit by bit, fantasy was being translated into blueprint. By the 1980s and 1990s, one might find, buried in a technical journal or mulled over at a futurist conference, serious papers on astroengineering and star-scale construction. Engineers calculated solar radiation pressure and gravitational forces to figure out where a Dyson swarm could orbit stably without falling into its sun or flying off into space. They debated the merits of rigid shells, quickly recognizing their dangers, versus dispersed swarms of independent satellites. They puzzled over how to dissipate the tremendous heat that billions of solar collectors would themselves generate. What had been a wild thought experiment was slowly becoming a subject of rigorous, if highly speculative, study. The language of "when we harness a star" began to crop up, not only in stories, but in scientific discourse. Even as these grand schemes were being laid out on paper, humanity was taking baby steps in the same general direction. Space agencies and companies launched more and more satellites, some for communications, some for observing Earth, and many carrying broad solar panels to power their electronics. Each new solar array, unfurling above the atmosphere, was a tiny affirmation of the Dyson principle. We were already placing machines around our star to drink in its light, albeit on a minuscule scale. Projects to build space-based solar power stations, collecting sunlight in orbit and beaming energy down to Earth, were proposed as a practical intermediate step. In these small ways, the Dyson dream was beginning to glint in reality. We were learning how to work in space, how to deploy swarms of devices, and how to harvest sunshine beyond the cradle of Earth. Still, the Dyson sphere remains, for now, in the realm of thought experiments and far future contemplation. The first detailed roadmaps have been drawn, but they are written in pencil, not ink, tentative and subject to revision as technology advances. As our capabilities grow, what was once pure fantasy edges ever closer to the conceivable. The conversation has evolved. It's no longer about if such a structure could exist, but rather how one might actually be built, given enough time and will. In that evolving conversation, the line between wonder and reality begins to blur. The dream that once lived only in imagination has taken its first steps into the laboratory and the workshop, even if only as prototypes and proposals. On the threshold between imagination and reality, the Dyson sphere stands as a grand question mark for our species. The blueprints exist in theory, waiting for the day someone dares to turn them into reality. The journey from wonder to workable plan has begun, but the journey from plan to colossal construction still lies ahead, unwritten. And so the story continues, as we edge ever closer to the day we might, in fact, wield the light of an entire star. The ultimate endeavor remains before us, its challenges and rewards unknown, beckoning a future generation to step forward and make the sun itself a home. A colossal hollow sphere embracing a star. It is an image both thrilling and haunting. This vision conjures a cosmic cathedral, with a sun captured at its center and shining eternally upon the inner walls. Science fiction tales have painted scenes of vast landscapes curving upward on that inner surface, a serene paradise lit by a captive sun. It is an idea that speaks to the ultimate conquest of space. A star made tame, its power fully enclosed by the hands of an advanced civilization. In daydreams born of these tales, one might imagine standing on that inner surface, looking up to see whole continents and oceans arching high overhead. There would be no night, only eternal day beneath a sun fixed at the center of the sky, its light evenly bathing every horizon. The available living area would be staggering, millions of times the surface of Earth. enough room for trillions of lives spread across an endless landscape under an unsetting sun. Such is the allure of a Dyson shell, a promise of near infinite space and energy, a celestial Eden crafted by intelligence. Yet for all this wonder, a Dyson sphere, in the form of a solid shell, remains a phantom, a structure that defies the basic rules of physics and materials. The deeper one looks, the clearer it becomes that a rigid sphere around a star would be inherently unstable and ultimately unattainable. The captivating dream of a sun-encapsulating habitat dissolves under the harsh light of physical reality. Gentle as it sounds to cradle a star in a shell, such a structure would find no gentle balance. Inside a perfect spherical enclosure, gravity offers no anchor. According to the laws of gravity, a uniform hollow sphere feels no pull from the star at its center. It floats freely, neither drawn in nor pushed out. The slightest nudge or imperfection would send the shell drifting, inevitably and disastrously. Without a force to center it, eventually part of that enormous sphere could spiral inward, colliding with the star it was meant to contain. And even if gravity could hold it, the sphere would be crushed by its own enormity. A Dyson shell spanning a whole orbit would have to support itself across unimaginable distances, resisting collapse at every point. The compressive forces of trying to arch over the sun are beyond anything our strongest materials could endure. Steel, carbon, even exotic alloys would buckle and snap under the stress of forming a rigid vault around a star. No known substance has the strength-to-weight ratio to maintain such a shell without caving inward or tearing itself apart. Beyond strength, consider the sheer amount of matter required. To build a shell, one astronomical unit in radius, the distance from the Earth to the Sun, you would need materials equivalent to planets upon planets. It has been calculated that even if every rocky world and metal-rich asteroid in the solar system were ground down for construction, the resulting sphere might only be a few inches thick at best. An entire system's bounty of iron, silicon, and carbon would yield just a delicate cosmic eggshell around the Sun. It is a staggering shortfall that underscores the futility of a solid sphere. Even if one somehow forged that shell, it would face constant peril. Meteoroids and comets, usually harmless specks in the vastness of space, would become high-speed bullets against an immense, unshielded wall. Each impact could tear gaping holes in the thin shell, and maintaining such a structure would be a never-ending battle. The Sun itself is not a quiet neighbor either. Solar flares and eruptions would hammer the inner surface with fierce radiation and showers of charged particles. A hollow sphere, so static and unyielding, might crack under these assaults, its utopian interior exposed to the vacuum once more. In truth, the original thinker behind this idea, physicist Freeman Dyson, never insisted on a literal rigid sphere. Dyson envisioned something more subtle, a swarm or cloud of countless smaller satellites and habitats absorbing starlight. Not a monolithic shell, but a myriad of pieces collectively catching the sun's light. The popular image of a solid globe took hold in fiction, but scientists understand that a static shell is the least practical solution. Reality pushes us toward more flexible, dynamic designs that can accomplish the same goal without courting impossible physics. So the iconic, hollow globe encasing a sun remains a beautiful impossibility. It serves as a symbol of ultimate ambition. Yet, as a blueprint, it fails. The laws of gravity and the limits of matter close that path to us. If a civilization is to truly harness the full brilliance of its star, it must do so not with one giant shell, but with many smaller pieces working in concert. From the ashes of that shattered sphere, dream emerges a new vision, Swarms, rings, and clouds of machines dancing around the sun, catching its light in a more feasible, if still fantastical, way. For a more attainable path, the sphere becomes not a single vessel, but a multitude. Imagine countless mirrors and solar collectors orbiting the sun like a shimmering cloud of fireflies. Each one is a separate craft, tiny compared to the star, but together forming an enormous array that intercepts sunlight. Instead of a continuous shell, we have a cosmic swarm, a Dyson cloud of machines, collectively drinking in the star's radiation. In this Dyson swarm, every satellite follows its own orbit. Some might circle along the sun's equator, others swing over its poles, creating a thicket of orbital paths crisscrossing in 3 dimensions. At a distance, their arrangement would resemble a diffuse sphere of moving lights, each glinting as it catches and converts solar energy. There could be thousands, even millions, of such units, gradually added over decades or centuries until the swarm grows dense enough to capture a significant fraction of the star's output. A simpler version of the concept begins as a ring, a band of satellites lined up around the sun's waist, like an artificial Saturn's ring encircling the light. This glittering ring world would mark the first step toward a full swarm, covering a narrow slice of orbital space. From there, additional rings and tilted orbits would be filled in, one by one, until the star is girdled in all directions. The final result is not a solid surface, but a dynamic, shifting sphere of machines, a Dyson swarm alive with orbital motion. An alternative approach forgoes orbits altogether and instead balances on the light itself. This is the Dyson bubble, a flotilla of statites, stationary satellites, each equipped with an immense light sail that holds it in place against the sun's gravity. Rather than circling the star, these mirrors and panels hover where they are, suspended by the ceaseless outward push of sunlight on their sails. With carefully tuned sail sizes and angles, a whole shell of such statites could float serenely around the star, each one locked in position by the delicate equilibrium of light and gravity. The beauty of the Dyson bubble is that its components remain fixed relative to the star and to each other, forming a more uniform sphere of collectors. There are no orbital crossings, no constant reshuffling of positions. Once placed, a statite stays at its station, keeping watch on the sun. But achieving this demands unfathomably light and strong materials for those sails. The gossamer wings must be thin and heat-resistant, yet broad enough to catch the sun's photon breeze and counteract gravity. At our current technological level, even our best spacecraft sails are far too heavy. The Dyson bubble belongs to a future of advanced materials. A statite's mirror might need to stretch for dozens of kilometers to balance even a modest payload against the sun's pull, a scale of construction that staggers the imagination. No matter the configuration, a Dyson assembly would gradually dim the face of its star. In the beginning, with just a few rings or clusters, most sunlight would still pour through the gaps. But as the project neared completion, the swarm could grow so dense that only stray beams of light slip between the orbiting collectors. In a perfected bubble formation, the coverage would be so uniform that the star's brilliant disk is entirely obscured from view. What was once a blazing beacon in the sky becomes a dark sphere, detectable only by a faint halo of infrared heat radiating from the myriad machines surrounding it. One can imagine journeying through such a completed swarm. A spacecraft approaching the sun would find itself among innumerable artificial structures, an entire archipelago of machines drifting in the void. The closer it came, the more the darkness of space would give way to a new kind of light, the glint of countless mirrors and habitats, shining with reflected sunlight and the glow of their own operations. The sun itself would be hidden behind this lattice of technology, casting the area in a strange perpetual twilight. All around, silent forms would slide along their orbits, an endless fleet of solar sails and power stations, each one part of the grand collective that now encircles the star. Whether swarm or bubble, these designs answer the riddles that doomed the solid shell. They break the colossal sphere into manageable pieces and allow empty space between, letting orbital mechanics or radiation pressure provide support instead of brute structural strength. The result is a flexible megastructure that can shift and breathe with the physics of the system. However, both concepts share a common necessity: extraordinary substances to build mirrors, sails, and support frames that can endure the unforgiving environment near a star. A megastructure around a star will live its life in a furnace. Close to the sun, the intensity of heat and radiation is mind-boggling. Sunlight can bake any exposed surface, and temperatures can soar to levels that would boil away water and melt many metals. The star pours out not only light, but also floods of charged particles and swirls of magnetic fields that can fry electronics and erode materials over time. Any satellite in this environment must be built of stern stuff, able to withstand a continuous onslaught of energy that never lets up. Finding materials that can endure these extremes is a puzzle for the ages. Our everyday substances wilt under such conditions. Conventional metal alloys weaken and deform in high heat, and electronic components struggle with constant radiation. The solar collectors of a Dyson swarm must survive years of unfiltered sunlight, radiation blasts, and drastic temperature swings as they move in and out of the star's glare. This calls for matter of exceptional purity and resilience, perhaps unlike anything we have crafted before. One candidate that excites scientists and engineers is carbon, not in its familiar forms like graphite or diamond, but reimagined at the nanoscale. Graphene, a one-atom thick sheet of carbon, boasts extraordinary strength and thermal stability. It could form the backbone of ultralight solar sails, or the structure of panels that never crack. Carbon nanotubes, rolled-up tubes of graphene, have tensile strengths that exceed steel by orders of magnitude, while being far lighter. Woven into composites, these carbon structures might produce cables and frames for Dyson sphere elements that handle immense stress without snapping. Equally important is withstanding the sun's heat. Future materials may need to remain solid and strong, even when heated to hundreds or thousands of degrees. Ceramic composites or refractory metals that keep their strength at red-hot temperatures could be essential for parts of the collectors that face the sun directly. Special coatings might reflect away harmful ultraviolet light or prevent charged particles from chewing into surfaces. Some designs could even incorporate miniature magnetic shields, deflecting the solar wind's charged particles to protect delicate electronics. And any absorbed energy must be dealt with. Each structure would include radiators on its shaded side to bleed off excess heat as infrared, glowing like a dim ember against the darkness. Meanwhile, on the dark side of these satellites, another challenge awaits: intense cold. Materials will have to endure being baked on one side while frozen on the other, all without cracking from thermal stress. Then there are the solar panels themselves, the surfaces that actually convert starlight to power. These need to be highly efficient, far beyond today's silicon photovoltaics. We imagine multi-layered cells using advanced semiconductors to soak up a broader range of the sun's spectrum, or perhaps entirely new methods of energy conversion that harness solar heat or particles directly. Whatever the technology, the materials must resist radiation damage. Maybe self-healing circuits that repair atomic-level flaws caused by high-energy particles, or redundant networks that keep power flowing even if some sections falter. The Dyson sphere's fabric must be as tough as it is clever. As we push the boundaries of material science, some proposals venture into the realm of the exotic. Engineers speak of metamaterials, designed microstructures with properties no natural substance possesses, like perfect reflectivity or superconductivity at high temperatures. Others imagine alloys infused with nanoparticles that continuously reconfigure to heal microcracks and resist fatigue. Perhaps even biological components could play a role. Swarms of microscopic robots or engineered microbes might roam the vast surfaces, detecting and repairing damage as it occurs. Such self-maintaining materials would give the Dyson sphere the longevity it needs to operate for millennia. In essence, building a sphere around a star demands materials that are light but immensely strong, heat-tolerant, and remarkably durable. It is a tall order that might only be met by technologies we have yet to discover. The search for these substances is ongoing in labs today, as scientists test new fibers, crystals, and composites that inch closer to the required performance. They are laying the groundwork for future generations who might weave these materials into giant solar sails and orbiting power stations. With the right materials in hand, the blueprint of a Dyson sphere comes one step closer to reality. But the challenge then becomes how to set those millions of pieces in motion and keep them there. Designing orbits for a Dyson swarm is like choreographing a cosmic ballet. Each satellite is a dancer, bound by the music of gravity, circling the sun in a predetermined rhythm. To avoid chaos, their movements must be carefully planned so that no two paths collide. Millions of objects moving at tens of kilometers per second, yet all must keep a harmonious separation. One misstep could send debris cascading through the system. Achieving this stable dance is essential if the structure is to persist for ages. In practice, this might mean dividing the swarm into distinct orbital families. Some collectors could occupy an equatorial band, orbiting in the same plane around the sun's middle, spaced out like pearls on a necklace. Others might take up tilted paths, sweeping over the sun's poles in long loops. By assigning groups of satellites to different lanes at slightly different altitudes or inclinations, engineers can ensure that these orbits don't intersect dangerously. Each ring or cluster moves on its own track, minimizing the chances of unwanted encounters. Even so, absolute perfection is impossible. With so many actors, near misses and minor perturbations will occur over time. How can chaos be averted among such a crowd of satellites? That is where active control comes in. Each solar collector would likely be equipped with small thrusters or adjustable sails to make tiny corrections, nudging itself back on course whenever it drifts. Guidance systems, perhaps AI-driven, could monitor thousands of orbital tracks simultaneously, issuing gentle adjustments to prevent any slow-motion collisions years before they might happen. In essence, the swarm becomes a self-correcting system, constantly tuning the dance of orbits to maintain order. One can envision a distributed intelligence permeating the sphere, a hive mind of machines communicating in real time to keep all components in line. For the Dyson bubble configuration, the challenge changes form. Here, satellites do not orbit, but hover, pinned in place by light pressure. Stability, for a statite, means holding a precise orientation of its sail at all times. If one statite tilts wrong, or its sail is damaged, it could begin to slip inward toward the sun or drift off station. To prevent that, each statite might use automated controls to tweak its sail angle or fire tiny jets to stay in position. They must also avoid blocking each other's light. If one statite were to drift directly behind another, it would slide into shadow and lose the very pressure that holds it aloft. A network of sensors and communication between neighbors could alert the whole ensemble to any unit deviating, allowing others to compensate or even gently nudge the straggler back into place. Long-term stability also means accounting for subtle tugs and nudges that accumulate over years. The gravity of remaining planets, if any are left, could gradually distort some orbits if unaccounted for. The slight but steady pressure of the solar wind might, over decades, push certain light structures off balance. Even the sun itself slowly loses mass as it shines, weakening its pull bit by bit. Random events, like a rogue comet slashing through the swarm or an unexpected meteor shower, could damage some of the collectors. The designers of a Dyson sphere must plan for these possibilities by giving the system resilience, orbits that can adjust to a shifting star, and control protocols that keep the swarm robust against drift or damage. They would need the capacity to swiftly replace or repair any unit that falters, and to sweep up dangerous debris, ensuring the overall web remains intact. In this intricate dance of gravity and light, the aim is permanence, or something close to it. The Dyson sphere's myriad components should be able to circle or hover around the sun for millennia without catastrophic failure. With sufficiently advanced automation, the entire system becomes like a self-sustaining ecosystem of machinery, adjusting to disturbances, rerouting around problems, and evolving to maintain stability. It is a man-made solar system in its own right, a vast clockwork of habitats and mirrors, replacing the old celestial order with a designed one. As long as the star burns, the machines around it can keep turning in an unending waltz, granting the civilization an almost immortal lifespan, basking in its star's energy. Yet none of this elegant choreography can even begin without raw materials and the will to build the dancers of this cosmic ballet. Constructing a Dyson sphere is not just a feat of engineering, but one of resource acquisition on a stellar scale. The raw material has to come from somewhere, and there is nothing modest about the demand. Building even a partial swarm would consume more metal and silicon than all of Earth's industries could produce in centuries. To gather such bounty, a star-building civilization must turn to the only sources vast enough: the planets, moons, and asteroids of its solar system. In essence, the Dyson project asks a civilization to literally break worlds apart for parts. A small, rocky planet, like Mercury, might be the first to go into the cosmic furnace. Mercury, rich in iron and heavy elements, and so close to the sun, is a prime candidate to be dismantled layer by layer. Automated mines could bore into its crust, vaporizing rock and extracting ores, while giant launchers fling those materials off-world. At first, the change is almost imperceptible. Thin streams of dust and metal ore lifting away from Mercury's surface into space. But soon, whole assemblies begin to take shape overhead as Mercury's substance is mined and sent skyward. The planet's riches are carried off in an unceasing succession. Iron, silicon, rare minerals, all ferried to orbital factories. Above Mercury, swarms of assembler drones take these shipments and fabricate them into the skeletons of new satellites. With each passing year, Mercury diminishes. Mountains and craters are carved away into raw materials, launched upward as glowing specks in the sunlight. Eventually, Mercury is little more than a memory, its remaining husk quiet and empty, its substance reborn as part of a great machine swarming the sun. The asteroid belt offers another treasure trove of building blocks. Countless rocks drifting between Mars and Jupiter contain iron, nickel, carbon, and water ice, a scattered warehouse of raw ingredients. Swarms of robotic miners could hop from asteroid to asteroid, chewing them down and processing the ore on site. Instead of one big world, this approach nibbles away at thousands of smaller ones, funneling resources to nearby assembly stations. Gradually, the rubble of ancient space rocks is transformed into structured panels, beams, and electronic systems that will join the growing swarm around the sun. Moving these materials is a challenge all its own. Conventional rockets would be far too inefficient for shifting planetary masses into orbit. Instead, engineers might deploy electromagnetic railguns or mass drivers, devices that use powerful magnetic pulses to catapult chunks of rock and metal off a world's surface and into space. Picture an enormous cannon on what was once a planet, rhythmically launching capsules of minerals into the sky day and night. These payloads would be met by robotic tugs waiting in orbit, ready to ferry the cargo to processing hubs. It is an industrial symphony, relentless volleys of resources rising from a doomed world to feed the creation of a sphere around the sun. As materials pour into space, assembly can take place in orbit where gravity won't interfere. Factory ships and construction drones would take delivery of the raw elements and turn them into functional structures. Sheets of solar cells could be printed or grown in zero gravity, unfurling like metallic petals. Mirror segments might be assembled piece by piece, each carried by small autonomous craft to its designated position around the star. Perhaps the builders would establish orbital shipyards the size of cities, humming with activity as they churn out component after component of the Dyson swarm. Newly minted satellites could then deploy their sails or ion drives and navigate to their assigned orbits, autonomously joining the ever-expanding constellation around the Sun. To manage such a colossal task, the builders would likely rely on self-replicating industry. The endeavor might begin with a handful of robotic miners and automated factories delivered to a rich asteroid or moon. These machines could use the first materials they extract to assemble copies of themselves, increasing their numbers geometrically. With each generation of new robots and drones, the pace of extraction and construction would quicken. Before long, a single mining outpost could grow into an army of mechanical workers, stripping resources at an astounding rate. In the final reckoning, hardly any part of the solar system would remain untouched. Even distant moons and comets might be hauled in to supply the remaining material. Even with such exponential growth, the project would span decades, centuries, or more. A slow consumption of worlds to feed a shining sphere. Bit by bit, landscapes are reduced to raw elements and then to precisely engineered components. The sacrifice is immense. Entire planets might vanish into furnaces and assembly molds, reappearing as an intricate lattice of satellites embracing the Sun. In the end, what remains is a transformed solar system, one in which planets are no longer the defining feature, but rather a vast construct of mirrors and machines, turning in unison around a captive star. From within, it is an empire of machines and energy. From outside, it appears almost like nothing at all, the star now wrapped in a veil, its brilliant light hidden from view. From a distance of light years, the completed Dyson sphere would not look like the grand structure it truly is. To a faraway observer, the star at the center might seem to have simply vanished. Its blazing light no longer streams into space. In its place is a faint warmth, an unusual excess of infrared radiation that hints something hidden is there. The sphere itself would be far too dark to see. It is the absence of the expected starlight that offers the clue. For such a star to disappear is a slow eclipse. Over decades, an outside observer would see its gleam gradually dim and redden as the sphere took shape, until finally the star's visible light was entirely choked off. The once brilliant sun would now be cloaked, shining feebly in visible wavelengths, but glowing softly in infrared like a banked coal. The countless panels and collectors intercept nearly every photon and put them to use, then radiate their waste heat gently outward. Seen from afar, this stellar enclosure would appear as a cool, dim object, a ghost of a star. Only by analyzing its spectrum carefully would one realize the truth. The star's energy is still there, but streaming out at lower energies, emitted by the technology that surrounds it. For the architects of this megastructure, the view from within is very different. From inside the swarm, they would see the inner faces of their myriad satellites aglow with captured sunlight, while beyond them lies the blackness of space, peppered with distant stars. Their sun has become a warm, diffuse glow on the inner surface of their artificial world, a steady, never-setting illumination that powers every aspect of their civilization. Under this perpetual daylight, life and technology flourish, fueled by the star's full output, bent to every need. From the outside, however, this engineering marvel betrays itself by that telltale infrared shimmer. Astronomers might notice the anomaly, a star that should be bright, but instead is inexplicably dim and wrapped in an infrared haze. Such an observation would set minds wondering, is this the mark of an advanced civilization cloaking its sun? Indeed, scientists today have proposed searching for exactly this sign. Stars that are oddly faint in visible light, yet warm with excess infrared. Potential evidence of cosmic engineering. In the silence of space, the completed Dyson sphere whispers rather than shouts, announcing its presence with subtlety. It is a quiet triumph. The sun that once blazed freely into the cosmos is now domesticated, its fierce brilliance subdued to a gentle afterglow. In achieving this, the civilization has traded the outward beacon of its star for an inner reservoir of power. The star's natural radiance, once visible across light years, is now contained and repurposed solely for their own domain. This infrared emanation is the final, gentle applause of a project centuries in the making. A star enclosed, a dream made real. Yet even in completion, it is not an end, but a beginning. With a whole star's power at their disposal, the civilization stands at the threshold of possibilities we can scarcely imagine. The Dyson sphere's glow is both the end of one journey and the dawn of another, one that continues beyond this achievement. On the Kardashev scale of cosmic advancement, enclosing a star heralds a civilization's ascent to Type 2, an epoch of practically boundless energy. To put this in perspective, the sun's output is billions of times greater than all the power human civilization consumes today, and nearly all of that is now at this society's disposal. But what will they do with such immense power? That remains the next chapter of their story. With their sun subdued and serving their needs, perhaps they will turn ambitious eyes outward, to distant stars, to deeper mysteries, to heights of existence we can hardly fathom. The Dyson sphere's gentle glow is not a finale. It is the opening of a new frontier, one that beckons beyond the star it so quietly enfolds. In the silent darkness near the star, a tiny machine wakes and opens its gleaming solar wings to the light. This solitary spacecraft is no larger than a humble house, yet it carries the blueprint of an entire civilization's ambition. It drifts in orbit with gentle purpose, absorbing sunlight and converting that energy into motion and mind. In its memory, banks lies a plan older than any one generation, a dream now ready to unfold in metal and light. After ages of preparation, the first autonomous factory now circles the sun in a slow, steady arc. It is a self-contained workshop of robotic arms and 3D printers, programmed to toil endlessly without a single human hand. Drawing on the power of starlight, it begins crafting the basic pieces of an impossible puzzle. Thin wafers of solar collectors emerge from its assembly lines, the first shiny tiles in what will become a magnificent mosaic around the star. But one machine alone cannot cage a star. Inside its metal hull, the pioneer's instructions unfurl, guiding it to create others of its kind, using the metals and minerals carried within or gathered from nearby cosmic debris. It assembles piece by piece the components of a twin. Robotic limbs work with patient precision, forging circuits, frames, and solar sails. In the void of space, a second factory is born, drifting free with a gentle push, ready to spread its wings and join the ceaseless construction. In the early days of construction, resources are precious and must be carefully gathered. The tiny factories turn their sensors toward a nearby asteroid, drifting in the sunlight, a primitive island of rock and metal. With quiet determination, a cluster of robots descends onto the asteroid's surface, digging into the ancient stone. They scoop and grind the regolith, extracting ores and elements, feeding raw matter into furnaces that glow like tiny suns against the darkness. Day by day, one factory becomes two, and two become four. Slowly, the lonely pioneer gains a small fleet of companions. Each new unit spreads out in its own orbit, yet all remain linked by invisible threads of communication and purpose. They share tasks like a colony of ants on a cosmic scale, each robot knowing exactly when to build, when to mine, and when to carry its precious cargo of newly minted parts into position around the sun. In the months that follow, a delicate constellation of mirrors begins to take shape. Dozens of shining panels unfurl and drift into their prescribed orbits, forming a sparse halo around the sun. From a distance, they resemble a swarm of fireflies, each one catching the sunlight and flashing it back in a silent celebration. This infant Dyson swarm is humble and thin, yet every glimmering speck heralds the dawn of a new era of light and industry. For all the glimmering progress, these first swarms are but a drop in an ocean of light. The star's power is vast beyond measure, and to seize more of it, the builders will need far greater resources than any asteroid can provide. The gaze of the project turns to a bigger prize: a whole planet. The innermost world of this system, scorched Mercury, now stands ready to be transformed, its very substance destined to become the fabric of a stellar megastructure. A lonely, airless world hangs close to the sun, its surface blasted by solar fire for eons. Mercury, small, searingly hot by day and bitter cold by night, has long been a silent witness to the sun's brilliance. Now, at last, this barren planet finds its purpose in the grand design. What was once a desolate rock is destined to become the seed of a sphere, its mountains and plains fated to be dismantled and reborn as shining panels in orbit. For untold ages, it has been lifeless and unchanging. But now, human ingenuity will rewrite Mercury's story entirely. For this monumental task, an army of machines descends from the sky. Countless landers set down on Mercury's scorched ground as dawn breaks over a cratered horizon. They come in all forms: giant digging automata, spider-like refineries, and swarms of tiny exploratory drones fanning out over the landscape. Under the unfiltered glare of the sun, these machines awaken and begin their quiet work, preparing Mercury for a careful, piece-by-piece disassembly. What was once a silent, dead terrain now teems with mechanical activity, though no living being walks there. Mercury's crust yields to the onslaught of automated mining. Colossal drills bite into the bedrock, cracking it into boulders and dust. Towering smelters shielded against the blinding sunlight, melt these rocks and separate metal from stone. Great mirrors, arranged on the surface, harness the sun's own ferocity, focusing beams to vaporize stubborn ore veins. In every crater and canyon, machines toil with methodical calm, reducing a planetary landscape into raw materials. Not all of Mercury's treasure is meant to stay on its surface. Along the planet's equator, networks of electromagnetic launch tracks take shape, gleaming like dark ribbons across the grey terrain. These mass drivers accelerate capsules filled with refined metal and freshly forged components, flinging them out of Mercury's gentle gravity into space. One by one, silent payloads lift off in steady succession, arcing into the void. Above, robotic ferries await to catch these deliveries, guiding them to their places in the growing orbital swarm. As months turn to years, Mercury itself begins to wane. What was once a spherical planet is gradually carved down like a vast sculpture under countless chisels. Deep mines and cavernous pits riddle its surface, and whole regions are stripped to their core. From space, the planet's shine dims as more of its mass is hauled away to orbit. Mercury is slowly vanishing, transformed piece by piece into an expanding cloud of man-made satellites around the sun. For every mounting ground to dust on Mercury, a new mirror sails in the heavens. By the time Mercury is reduced to a mere shell of itself, millions of new satellites glint in solar orbit. The innermost planet's sacrifice has given birth to a powerful swarm capturing the sun's energy. In place of a lifeless rock, there is now a bustling congregation of machines bathing in starlight. To the watching civilization, this sight is both triumphant and poignant, an ancient world diminished so that something new could rise in its place. The true marvel behind this cosmic construction is not only the sheer mass of material, but the intelligence and automation guiding every step. From a handful of machines has grown a vast population of robotic workers, multiplying their ranks with each passing season. What began as a few lonely pioneers is now an autonomous ecosystem of industry, humming with activity from Mercury's gutted surface to high orbital assembly lines. No human could micromanage the millions of tasks unfolding in tandem. It is the silent choreography of artificial minds that keeps each unit on course. At the helm, sophisticated artificial intelligences oversee the project, adjusting plans and solving problems in real time. Though millions of individual machines toil, they move with one purpose, like a single colossal swarm. They communicate constantly, sharing data on trajectories, construction status, and resource needs in the blink of an eye. Like a beehive or an ant colony, each member performs its role without grasping the entire blueprint. Yet together, they manifest the grand design. If one unit finishes its task or falls behind, others automatically shift to fill the need, guided by a distributed intelligence. This swarm intelligence is the backbone of the cosmic industry here, robust, flexible, and tireless. In time, the machines even manage their own upkeep and propagation. They assemble new copies of themselves whenever more hands are required, and they cannibalize obsolete units to recycle materials. A drone damaged by a micrometeoroid is swiftly replaced and its components reprocessed, wasting nothing. Every element of the workforce regenerates, ensuring that the great endeavor never falters due to wear or loss. In this way, the construction effort sustains itself, a living, automated chain of creation, renewing its strength continuously. In the void above, the placement of each collector is a carefully choreographed ballet. Every new solar panel must slip into orbit among thousands of others, never colliding, never shadowing its neighbors at the wrong time. The guiding intelligences calculate precise trajectories and timing, and the machines respond with flawless precision. They fire subtle bursts of propellant to nudge themselves into exact positions, each panel joining a shimmering lattice that traces the sun's outline. From afar, this dance of mechanical fireflies is eerily graceful, a silent cosmic waltz governed by mathematics and foresight. In the beginning, new satellites emerged only slowly, a few dozen in the first years. But now, production surges in the thousands and millions. Each generation of machines builds the next at a faster pace, and each ring of collectors begets the energy to forge more. The process feeds itself in a breathtaking loop. More energy yields more machines drive faster construction. What once grew cautiously now expands exponentially, until the space around the star is abuzz with construction on a monumental scale. As the swarm thickens, the very face of the sun begins to change. A web of technology now intercepts a significant share of its rays. The once unbridled solar brilliance is being tamed, channeled into countless converters and grid arrays. Seen from afar, delicate filaments of shadow and light now crisscross the star, signaling that this immense expansion is reaching its zenith. A vast portion of the sun's output is no longer streaming freely into space, but is captured and put to use. What started as a thin ring of devices has grown into a layered nest of orbits. Collectors circle at different inclinations and radii, forming an intricate three-dimensional net that ensnares sunlight from every angle. Overlapping paths carry millions of modules in synchronized harmony, so that at any given moment, some part of the swarm is soaking up photons that once would have escaped. The Dyson swarm has become a complex web, more intricate than Saturn's rings, yet engineered for a singular purpose: to drink in the star's power. For a project of this scale, even the distant frontiers of the solar system are drawn in. Fleets of automated freighters shuttle between worlds, ferrying supplies and parts where they are needed. Space stations and shipyards orbiting Jupiter and Saturn produce specialized components, while refineries on moons and in asteroid belts churn out fuels and rare elements. Nearly every colony, every outpost from Mercury to the Kuiper Belt, contributes its labor or resources to the Dyson swarm's growth. The entire civilization is galvanized, transformed into an interplanetary assembly line with the sun at its center. With the Dyson swarm's rapid growth comes the challenge of coordination on an unprecedented scale. Managing this endeavor requires every region and faction to work in concert. The complexity of orbits, resource flow, and assembly schedules demands a united effort stretching across millions of miles. It is a test of unity, one that civilization must pass in order to see the grand vision through. As the luminous web around the star expands, so too does the understanding that only together can this colossal dream be realized. An enterprise so vast has reshaped how humanity governs itself. No single nation or corporation can lay claim to the Dyson sphere. It is the common heritage of all humankind. To steer the project, a grand council of representatives forms: engineers, scientists, and leaders from every major world and habitat, all brought together to chart the course of building around the sun. Old rivalries are set aside under the pressure of necessity. In this newfound orbit of collaboration, humanity at last moves largely with one will, at least for this singular purpose. A sophisticated communication web knits the far-flung society together. High-bandwidth lasers and quantum communicators connect Earth to Mars, to the Jovian moons, and beyond. Minutes-long delays between planets become a tolerated heartbeat in the decision-making process. Every blueprint, every status update, every piece of news flows through this network, shared transparently, so that each colony and station knows the state of the whole. There is no single control center. Instead, coordination is distributed, synchronized by the constant exchange of information and a shared commitment to the mission. When unexpected challenges arise, they are met collectively. If a glitch halts a batch of solar sails unfurling near Venus, the alert echoes across the system. Engineers on Earth consult with robotic overseers on site. Specialists on Lunar and Mars pore over telemetry in real time. Within hours, a solution is devised. A software patch, a recalibration, a swarm of repair bots dispatched, and the issue subsides. No setback is faced alone. Every obstacle is tackled by minds and machines working in unison, no matter the distance. The project endures year after year, outlasting political cycles and personal careers. To keep it on course, humanity has had to learn patience and long-term thinking. An engineer who helped design the first solar factories may not live to see the sphere completed, but their children and grandchildren carry on the work. Schools teach the principles of orbital construction and energy management, preparing new generations to continue what was begun. The Dyson sphere ceases to be merely a project and becomes a permanent ambition of civilization, a shared endeavor that defines an era. Across the solar system, people find new ways to contribute. On Earth, factories build the delicate circuits and vast sails that will become the sphere's skin, while everyday citizens conserve energy to channel extra power to launch systems. On Mars, metallurgists and machinists proudly turn the planet's iron into girders and frames for the orbiting collectors. In the asteroid belt, autonomous miners and refiners supply rare elements for superconductors and quantum nodes that orchestrate the swarm. Even on far-off moons and stations, communities cheer as they watch live feeds of shimmering panels being installed, each feeling a personal stake in the creation growing around the sun. To prevent conflict and confusion, strict protocols ensure fair sharing of resources in space. If one region falls behind, others lend support. If a particular material grows scarce, new plans divert shipments from less critical projects. Shipping routes between planets are carefully managed so that the constant flow of parts and fuel moves without bottleneck or accident. Competition is replaced by coordination, an economy of mutual aid overseen by the collective administration that has become the norm. Trust and transparency, more than laws alone, keep the machinery of cooperation running smoothly. In striving to encircle a star, humanity has also unwittingly forged a stronger sense of itself. The enormity of the task has cast old divisions into shadow. Disagreements that once seemed insurmountable are dwarfed by the scale of a sun-spanning construction. By focusing on a goal so immense and universal, people everywhere have found common ground. The Dyson sphere, as it rises, reflects not only engineering prowess, but an unprecedented unity, a shimmering bond that links millions of minds and hands in a single, shining purpose. It happens almost gently. At first, only instruments notice that something new graces the inner solar system's light. But soon, at dusk on Earth, as the sky darkens, a soft band of radiance appears along the horizon where the sun has set. It is not the glow of the sun itself, yet it shimmers with a faint golden hue. People around the world look up in astonishment as a subtle second twilight blooms overhead. The countless mirrors of the incomplete Dyson swarm are catching the sun's rays and reflecting them outward, creating a ghostly gleam in the evening sky, the first sign of the star's new ornament. Night after night, the glow grows stronger, until one evening it clearly outshines Venus, the once brightest point of light. In place of the evening star, there is now a diffuse aurora encircling the fading sun's location. A man-made twilight. For the first time, an artificial structure has become one of the brightest objects in Earth's heavens. Those shimmering arcs of light confirm that the Dyson network has reached a critical mass, its collective radiance surpassing that of any planet. The star's mirror has been born, announcing itself with a gentle, persistent shine. Across the solar system, celebrations erupt in recognition of this moment. On Earth, cities dim their lights so that people can gather under open skies, marveling at the ethereal glow of the swarm. On the moon's colonies, families press their faces to dome windows, watching a halo that was not there a decade before. There is a swell of emotion, pride, astonishment, even a trembling of reverence. Under that pale band of light, humanity sees concrete proof of its collective will and imagination. What was once a mere idea now hangs above them, serene and undeniable. Yet even as the partial Dyson sphere shines, it also casts new questions forward. Out beyond our system, any curious observers would see our sun's pattern of light change, a subtle beacon marking the presence of intelligence. We too must reckon with what we have created, nearly boundless energy, and the responsibility that comes with it. Our star now bears the fingerprints of our ambition, raising profound possibilities. With the sun's power finally within reach, the choices of how to use it, to reshape worlds, to explore deeper into the cosmos, to elevate every life, all open up before us, challenging and exhilarating. Under the glow of the star's mirror, one chapter of our story closes and another begins. This achievement, years in the making, is not an end, but a threshold. The Dyson swarm is still growing, and with it grows the promise of a future defined by abundance. Standing in the soft, new nightfall light, the people of this civilization know that they have reached a turning point. The path ahead is flooded with the light of a captured star, and where it will lead them is a tale still unfolding, a journey that continues beyond this moment, into a dawn of unimagined potential. As the last panel slid into place around the star, the Dyson sphere became a complete shell of radiant metal and glass, enclosing the sun in a cosmic embrace. The emptiness of space outside fell away, and within this new world, a soft, golden light bathed every surface continuously. What once was a sky speckled with distant stars was now a vast ceiling of engineered panels, gleaming with the captured luminescence of a star. There is no dusk here, no dawn, only an endless gentle day, warm and bright, stretching out to every horizon within the sphere. In this creation of ingenuity and ambition, a civilization awakens to a world without night. Life under perpetual daylight changes in subtle and profound ways. In the absence of a setting sun, the rhythms that once guided life have to be reinvented. Without natural nightfall, the people living inside the Dyson sphere teach themselves when to sleep and when to wake, guided not by the sky, but by their own design. They draw their curtains and dim their environments at chosen hours, creating an artificial twilight so their minds and bodies can find rest. This deliberate invention of night, a gentle darkness drawn across windows and streets at appointed times, becomes an essential ritual of life. For the early settlers of this sun-wrapped world, adjusting to unending daylight was both awe-inspiring and daunting. Many found themselves wide awake at what would have been midnight, their bodies stirred by the perpetual glow. In those first months, sleep came uneasily, and some souls grew weary under the tyranny of constant day. Doctors and scientists observed the strain and worked with engineers to introduce a remedy. Vast adjustable panels high above that could tint the sky. By programming sections of the Dyson sphere's inner surface to gently dim, they crafted a semblance of evening across cities and countrysides. This engineered dusk fell like a soothing veil, signaling to all living things that it was time to unwind. With this innovation, the people gradually tamed the endless day, teaching it when to imitate a setting sun. Even the quality of the light was carefully managed to ease the transition into this new era. The raw intensity of a star captured at close quarters needed tempering for comfort. So the light that reaches the inhabited lands is diffused and warm, not harsh. In the morning hours, designated by each community, the illumination takes on a soft golden hue, growing brighter and whiter towards midday. Later, before an artificial night, the glow subtly mellows, casting long, gentle shadows and amber tones reminiscent of late afternoon on old Earth. These shifts in light color and intensity help minds and bodies know what the clocks already declare, that one phase of the day is ending and another will begin. The entire environment is orchestrated to provide cues that once came naturally. A human-made symphony of light and shadow, guiding life's daily rhythm. With no real stars visible in a dark sky, the inhabitants craft new symbols to mark the passage of time. Soft chimes, or shifting ambient lights, indicate the equivalent of morning and evening. The concept of hours, days, and years still exists, but it is measured by clocks and by consensus, rather than by the movement of celestial bodies overhead. For older generations, who remember the cycles of an open sky, it is a strange adjustment. They recall the comfort of seeing the sun dip below a horizon, the quiet of midnight, the guiding constellations. For the younger ones born to the sphere, the endless light is simply home, and darkness is an experience that must be simulated or imagined. The plants and animals carried into this luminous world also adapt in their own ways. Under an eternal noon sun, some plants grow continuously, their leaves always turned toward the radiance, never folding in sleep. Gardens can produce food in abundance, with no winter or night to slow growth, though farmers find that some species still require periods of shade to truly flourish. And so they oblige, using great floating screens that drift overhead to cast moving shadows across fields in a slow, deliberate dance. These artificial shadows sweep over the landscape like clouds, granting intervals of respite to crops and creatures below. In forests that have been planted within the Dyson sphere, animals learn new patterns. Nocturnal species find refuge in dense groves or caves, places where the constant daylight is gentled to darkness. Birds no longer migrate with seasons, but perhaps with the ebb and flow of human-engineered light cycles that mimic spring and fall in certain regions of the sphere. Each ecosystem inside this shell of light is carefully tended, given a cadence of illumination and darkness that keeps it healthy. Nature, though contained, is still respected. The keepers of this world ensure that even in a realm of perpetual day, every living thing finds its rhythm. For humans, the concept of a sky has transformed. Where once they looked upward to a black expanse sprinkled with stars, now they see the inner surface of their own creation, arching overhead, faintly shimmering. If one gazes up, one might discern the grid of solar collectors and energy conduits high above, glinting like a subtle mosaic of mirrors. There are no stars visible beyond. The Dyson sphere captures every ray of the sun and leaves the outside universe hidden behind its veil. Yet the desire to connect with the cosmos remains. Some people, in moments of nostalgia or curiosity, visit special observatories at the sphere's inner surface. These observatories have small controlled apertures or screens that can display a view of the outer cosmos, allowing the inhabitants to witness the true night sky beyond their world of light, if only in simulation. Such glimpses of darkness and starlight are cherished, and the first time children raised entirely inside the sphere see a panorama of the Milky Way projected in a darkened dome, they fall silent with wonder. In a world without natural night, human culture evolves to fill the void left by darkness. Festivals emerge where entire cities agree to turn off the lights for a while, plunging neighborhoods into a comfortable dusk. In those moments, people walk under a sky of their own making, where lanterns or bioluminescent sculptures replace the missing moon and stars. They relish the novelty of seeing shadows stretch and candlelight flicker. Simple experiences that had been routine in humanity's past, but now feel almost magical. Through these communal nights, the value of darkness is remembered and honored, even in a civilization defined by its capture of endless daylight. Sleep itself becomes a conscious art form. Music and gentle narration guide the mind toward rest when the external world offers no cue to close one's eyes. Some homes are built with chambers that mimic the fading colors of a sunset on their walls when it is time to sleep, cycling through amber and purple hues into deep blue until the occupants drift into slumber. In the morning, these chambers brighten slowly with golden light, simulating a dawn that never naturally comes. Thus, the cycle of day and night persists, not by necessity, but by choice and creativity, a testament to how life adapts, even in unprecedented conditions. Throughout the sphere, there is a sense that time itself has softened. Without the strict demarcation of daybreak or nightfall, hours blend gently. People find they can work or play at any time beneath the steady glow, as long as they carve out moments for rest. Some communities choose to follow traditional 24-hour cycles, coordinated by light signals and public clocks that dim or brighten the local environment in unison. Others experiment with longer days, perhaps 30 hours or more, enjoying extended periods of activity followed by extended sleep, taking advantage of a sky that never forces their hand. Yet even in experimentation, a balance is needed. The human body and spirit still need rhythm. So the inhabitants listen to their inner clocks and to the advice of biologists and physicians who study life under eternal light. They learn that creating pockets of night is important for health, both physical and mental. Workplaces institute gentle lighting that shifts color and intensity over time, giving workers a sense of progression through a day. In schools, children's classrooms slowly dim in the afternoon to signal the approach of an artificial evening, helping young minds unwind. All these adjustments create a tapestry of life that thrives without natural night. It is a new chapter of civilization, where ancient instincts meet cutting-edge innovation. The people living within the Dyson sphere do not simply endure the loss of night. They transform the concept of night into something malleable and intentional. In doing so, they remain in touch with their humanity, the need for rest, for reflection, for the contrast that darkness once provided. And as they adapt, the endless day outside becomes less of a disruptor and more of a gentle background presence, like a quiet heartbeat from the star that now belongs to them. Beneath the artificial sun, life flourishes in abundance. The Dyson sphere's inner realm offers a vast canvas for ecosystems to grow and evolve, free from the old limits of night and cold. Green landscapes stretch farther than the eye can see, illuminated by a gentle, ceaseless daylight. In this nurtured world, plants soak up energy without pause, and forests expand across terrains once barren. The sphere's interior is so immense that it could hold hundreds of millions of Earths, and across this expanse, every inch is alive with the hum of an ecology powered by a star. On endless plains of wheat and rice, farmers gather harvest after harvest. Crops bathed in continuous light grow taller and fuller than on any open planet, yielding grain in quantities once thought impossible. There is no true winter to halt the cycle, only the seasons that humans choose to create. With careful planning, they alternate periods of growth and regeneration, using shading systems to give fields a rest when needed. Hunger has become a relic of history here. Food is plentiful and available to all, a direct dividend of the captured sun. Abundance extends beyond the farms into every corner of the biosphere. In orchards and greenhouses, fruits ripen in perpetual summer, and vegetables reach maturity in record time, nourished by soil enriched with recycled nutrients and constant warmth. Should any crop struggle, technology provides a gentle assist. Automated drones tend to plants day and night, though night exists only by design, pollinating flowers and pruning away wilt. The result is a world where nature and machine collaborate seamlessly, ensuring that none go without. Meals are feasts of fresh produce and cultivated delicacies, a daily celebration of living in a fully powered Eden. In this engineered paradise, weather itself is crafted with intention. Without natural day-night cycles or an axial tilt to create seasons, the architects of the sphere had to invent their own climate patterns. They learned to choreograph winds and rains by adjusting the flow of energy across regions. For instance, in one expanse, they might dim the solar panels slightly at regular intervals to cool the air, allowing clouds to form and drift over golden fields. In another, they let the light blaze a bit stronger to fuel a tropical monsoon, keeping rainforests lush and rivers full. Every breeze that blows and every shower that falls is guided gently by an unseen hand, maintaining balance in this world of perpetual day. The inner surface of the Dyson sphere is shaped not just by light, but by land and water, sculpted for a harmonious climate. Towering mountain ranges, built from the very materials of dismantled planets, rise up and create natural divisions between regions. These mountains catch the roaming clouds, releasing rain that feeds great lakes and flowing rivers. On the leeward side of the ranges, drier lands spread out, forming deserts and savannas that are nevertheless nurtured by human design when needed. Vast oceans, drawn from icy comets and ancient seas, have been poured into basin-like depressions across the sphere's interior. Their currents are guided subtly by energy fields, ensuring that even the seas have gentle tides and a circulation that keeps them rich with life. These oceans serve as the lungs of the Dyson world, absorbing warmth during the constant day and releasing it slowly when the light is dimmed, thus softening climate extremes. Within their stable waters, marine life flourishes. Great schools of fish and roaming leviathans thrive in ecosystems that know no winter, only the endless cycle of plenty. Variety is key to a thriving ecology, and so this artificial world is divided into myriad biomes. There are sections where, by deliberate choice, a cooler winter is simulated each year. In those regions, for a time, the light dulls to a softer glow, and the air grows crisp, prompting trees to shed leaves in hues of gold and red. Elsewhere, near the equatorial band of the sphere's rotation, a constant summer reigns. Jungles thick with foliage climb skyward, never losing their green. The transitions between these zones are gradual and carefully planned, as gentle as the twilight that people create each day. Life across the sphere experiences a rich tapestry of climates, all orchestrated under the steady heart of the sun. Even the sun's temper is kept in check for the sake of life within the sphere. The raw power of solar flares and storms is smoothed by layers of technology lining the inner surface. If the star surges in brightness or emits a burst of energetic particles, the Dyson sphere absorbs and redistributes that energy before it can upset the tranquil climate inside. To the inhabitants, the sun is ever steady and benevolent, a constant beacon of light that never burns too hot nor wanes too cold. In taming the star's whims, the civilization ensures that their artificial Eden remains secure and stable, untroubled by the tempests of the wider cosmos. Energy flows through this world like blood through a living being. The light captured by the sphere is converted into power and sent wherever it is needed, making the entire environment a web of vitality. Invisible beams carry energy to distant settlements, and superconducting pathways under the ground distribute warmth during the sphere's gentle nights or cooler seasons. Water is pumped over mountains to irrigate high valleys, drawn effortlessly by solar-powered engines. By day, or what passes for night, the lights of human dwellings never falter, and the hum of life, insects chirping, machines whirring softly, trees rustling in climate-controlled breezes, continues unbroken. With limitless energy at their disposal, the inhabitants have achieved a level of sustainability that old Earth could only dream of. All waste, whether organic or technological, is collected and broken down using processes that are now trivial to power. What was once rubbish becomes raw material for new construction, new goods, or fertile compost for farms. Factories run on captured sunlight day and night to replenish supplies. Nothing is truly scarce except what is deliberately kept rare for tradition or aesthetics. The sphere is a closed loop where everything circulates: water, air, nutrients, continuously purified and renewed by systems fed with the star's endless output. In this way, the environment remains pristine. Progress no longer carries the price of pollution that it once did. What was harm and waste in former times is now just another part of the cycle of creation and reuse, powered by the generosity of the sun. Unchained from natural limits, even the ambitions for preserving and enhancing life have grown. Biologists and ecologists use the plenitude of energy to nurture species that once hovered on the brink of extinction, or to introduce entirely new creatures thoughtfully bred for this world. In lush valleys, animals that died out ages ago on distant Earth roam once more, their genomes reconstructed and given a second chance under an eternal sun. Fantastic gardens bloom with flowers engineered to thrive in constant daylight, painting the landscape with colours beyond any rainbow. Every life form is part of a grand experiment in abundance, a proof that with enough energy and care, an ecosystem can become whatever one dreams it to be. Across open plains roam herds of creatures larger than any seen before, supported by the abundant vegetation. In the seas, coral reefs stretch for hundreds of miles, their growth accelerated by nutrient cycles that never pause. Birds fly through the bright sky without ever knowing a day of rainstorm or a night of chill darkness. Their patterns of migration are guided by innate instinct and subtle cues from the environment's design. Humanity, too, has adapted its role in nature. As gardeners of this vast world, people oversee the balance, stepping in only when necessary to fine-tune what the artificial sun provides. It is a gentle stewardship, born out of respect for life and confidence in technology. Amidst all this natural splendor stand the works of human hands. Scattered across the landscape, one finds cities and towns basking in the perpetual glow. They gleam with reflected sunlight, appearing as clusters of radiance nestled between forests and hills. The energy that flows so freely through the soil and sky is the same energy that lights their streets and powers their homes. Because power is never a concern, these settlements can be built with comforts and wonders once reserved for dreams. Fountains that never cease to flow, public gardens under climate-controlled domes, transportation networks gliding along invisible currents of magnetism. Each city is a beacon in the daylight, a mirror catching the sun, living in harmony with the green world around it. The boundary between the ecological and the artificial is soft and blurred in this civilization of light. Parks and wilderness areas thread through every urban center, and farms often sit atop the rooftops of skyscrapers, irrigated by automated systems and warmed by the sun captured above. Likewise, elements of nature are engineered. Towering trees that also serve as solar collectors, or fields of algae in transparent ponds, generating biofuel as a backup reserve. Standing in this world, one has the sense that everything is interconnected and nourished by the same source. The star at the center has become the heart of a great living organism composed of metal, flesh, and leaf. And as day never truly ends, the achievements of humanity shine without end as well, side by side with the thriving wild. In this realm of perpetual light, the environment and civilization coalesce into a single thriving tapestry. The forests, the fields, the oceans, and the shining cities all exist in a balance crafted with endless energy and endless care. The lessons learned over generations guide this balance. Technology must serve nature as much as humanity, and in turn, nature rewards civilization with beauty and vitality. So the world within the Dyson sphere sings with life, a song powered by a star and conducted by wisdom. And as we leave the plains and forests and draw closer to those gleaming cities among the mirrors, we prepare to witness how human innovation itself has been transformed by living under a captive sun. We arrive at a city of light, nestled under the constant noon sky. From afar, its skyline sparkles as if dipped in molten gold. Towering skyscrapers stretch upward, their glass and alloy exteriors gleaming, each surface catching and reflecting the brilliance of the encircled star. There is a breathtaking clarity to the air. Without the cycle of sunrise or sunset, the city stands in perpetual daylight, every contour sharp and every color vivid. Yet despite the endless day, the city does not feel harsh or overbright. It is suffused with a gentle luminance, carefully managed and kind to the eyes, as if the whole metropolis were built inside a soft golden morning. Architecture here has evolved in response to a world where energy is limitless and night never falls. Buildings are adorned with dynamic panels that can shift from transparent to opaque in an instant, giving residents control over light and shade. During the community's chosen night hours, these panels tint to a soothing twilight hue, and across the city, windows dim in unison, as if an invisible dusk has swept through the streets. When full daylight returns by collective agreement, the panels clear again, revealing blue sky and the ever-present sun. In this way, the design of every structure honors both the power of the star and the human need for balance. The materials of the city glint and shine, echoing the mirrors that line the Dyson sphere's inner surface. Many rooftops and plazas are fitted with reflective mosaics that redirect sunlight to where it's needed, or shield areas that need cooling. Some structures even incorporate colossal mirror arrays that move gently throughout the day, focusing light into energy collectors, or shifting brightness away from busy thoroughfares at midday. Walking down the streets, one can sometimes catch the flare of a distant mirror adjusting far above. A brief starburst as sunlight glances off its surface. These constant, subtle motions high in the sky remind every citizen that they live inside a grand machine of light, one that hums constantly in the background of daily life. City streets themselves are alive with this gentle power. Transparent roadways collect solar energy during the day, glowing softly beneath pedestrians' feet at night to light the way. Vehicles move quietly along them, most making no sound at all, propelled by magnetic rails or silent electric drives drawing on the star's gift. Public fountains throw arcs of water into the air, their pumps tirelessly powered by solar reactors, so the water never ceases its dance. Even on the hottest days, shaded parks and boulevards remain cool, as grids of mirrors redirect excess heat away, and reservoirs of energy run fans or misting systems to keep the climate pleasant. In every corner of the city, the abundant energy is at work, usually unnoticed, ensuring comfort and ease. Freed from utilitarian constraints, architecture becomes an art of imagination. There are towers, shaped like spirals, twisting toward the heavens, their surfaces covered in living green walls, fed by automated irrigation and constant light. Vast, domed pavilions house entire forests within, with climates carefully maintained so that one can wander from a tropical jungle to a temperate woodland in a few footsteps. Such feats of design exist purely for delight and wonder, made possible by unlimited energy and resources. Museums, universities, and concert halls sprawl without concern for energy costs. Their grand interiors are illuminated by sunlight piped through arrays of lenses and mirrors, or by ambient panels that glow like captured starlight at all hours. Each structure in the city is a statement, a celebration of creativity, fueled by the assurance that power is no object. Public spaces likewise overflow with fountains, gardens, and art installations, since nothing in design is constrained by cost or scarcity. On the outskirts of the metropolis, soaring above its districts, stand enormous constructs that serve as both art and infrastructure. Solar spires, hundreds of meters tall, rise like crystal obelisks, collecting and transmitting energy to far-flung communities beyond the horizon. Some of these towers double as transportation hubs, where electromagnetic elevators and aerial vehicles dock, all powered effortlessly by the sun. For travelers, ascending one of these spires is like riding a pillar of sunlight into the sky. Between the districts, shimmering bridges are suspended high in the air. Their cables gleam in the perpetual sun, and these sky bridges carry commuter pods that glide from one part of the city to another, never slowing for lack of energy. Every movement, every connection in the urban landscape seems to float on a cushion of light, unbound by the weight of fuel or the pull of gravity's usual limits. In the markets and streets below, life takes on a leisurely rhythm under the perpetual day. Cafes spill out onto sunlit plazas at all hours, shaded by intelligent canopies that follow the sun's angle to provide comfort. People stroll through bazaars filled with goods crafted from an abundance of materials and energy, fabrics that shimmer as if woven from sunlight, foods grown in vertical farms that tower just behind the marketplaces. There is music in the air, powered by unseen solar generators and cooling breezes are guided through the avenues by subtle environmental controls. With basic needs met without struggle, the city's inhabitants devote themselves to pursuits of art, knowledge, and community. Everywhere you look, people are painting murals on bright walls or gathering in parks to read and converse, their faces serene in the warm light. Creativity and learning flourish in every corner, unhindered by want or worry. The everlasting afternoon encourages a gentle pace, where time is measured more by the heart's contentment than by any clock. Despite all the technological wonders, the city retains a natural soul. Trees line every boulevard, their leaves soaking in the same light that feeds the skyscraper's solar grids. Birds nest in specially designed alcoves on high-rises, their songs mixing with the quiet hum of the city's systems. Waterways wind through downtown, reflecting the bright sky. They are part of an elaborate recycling system that purifies water with solar-powered filters. Yet they appear simply as serene rivers, where children play and commuters boat to work. Gardens bloom on rooftops and balconies, overflowing with flowers and fruit. Automated caretakers tend many of them, but these green spaces are also lovingly cared for by human hands. This blending of nature and design means that even in a vast city, one is never far from greenery or the calming sound of water. The result is an urban life that feels connected to Earth's timeless rhythms, even under an alien sky of eternal day. Every evening, or what the citizens agree to call evening, the city undergoes a gentle transformation. As the building panels tint to amber and purple, soft lights awaken along the streets. Holographic displays and art installations that lay hidden in daytime begin to glow, powered by energy stored during the long hours of light. Some project constellations onto the domed ceilings of public squares, recreating a starry night sky for all to share. Other installations illuminate sculptures and fountains with slowly shifting colours. The city does not grow truly dark in this artificial night. Instead, it shifts to a subdued palette, like a collective sigh of relief after the day's activity. Under this made twilight, people dine on open-air terraces and gather on balconies to watch the play of lights. They experience a restful ambience that their forebears once found under natural stars, now created anew by human ingenuity. In those moments, the difference between a real night and an invented one seems to melt away, leaving only peace. As the cycle continues, morning comes not by the sun's rising, but by a slow brightening, orchestrated by the city itself. Before long, the panels clear to transparency, the holographic stars fade, and the full glory of the real sun reasserts itself across every rooftop and park. This self-made rhythm of day and night gives the city a gentle heartbeat amid the permanent sunshine. It also underscores the mastery the civilization has over its environment. Even the coming of night is now an act of choice, a communal creation rather than a cosmic decree. In these gleaming urban habitats, the relationship between humanity and their star is woven into every facet of existence, conscious and harmonious. Looking out from one of the highest towers at midday, one can see beyond the city's edge to the vast landscape that surrounds it, all under the same unblinking sky. Scattered glints on the horizon mark other towns and reflective installations catching the sun. The whole world seems like a mosaic of light and life extending to an unfathomable distance. Here, at the city's pinnacle, a viewer might reflect on how far civilization has come, from cities that once burned coal and gas for warmth and light, to this metropolis, where an entire star's energy is at their fingertips. It is a triumph, visible in every sparkling surface and thriving street below. And yet, amid this splendor, there is a quiet recognition that not all challenges are solved by light alone. In the cafes and lecture halls, in the theaters and temples of the city, conversations often turn to questions of purpose and value. When energy and material scarcity are erased, what motivates a life? What new arts, philosophies, or dreams arise when no one must toil for mere survival? The city's very ease forces introspection. In this shining place, where nearly every want can be fulfilled by technology and power, the citizens seek to define new frontiers of meaning. This is the weight of abundance, a subtle, existential gravity that now draws their minds and spirits, even as their physical world has been unshackled from traditional limits. Thus, the cities among the mirrors stand not just as testaments to engineering and wealth, but as crucibles for culture and thought. Each glowing avenue and tranquil courtyard becomes a space for exploration of the human condition under unprecedented conditions. Music, debate, and innovation thrive here, fueled by the freedom that the Dyson sphere provides. As we leave the bustle of the sunlit city and step back to observe, we see a civilization basking in the light of its achievements, yet also casting long inward shadows, questioning how to grow and where to aim next. In the journey from scarcity to abundance, the outward transformation is nearly complete. Now comes the transformation within, as we shall see. In this world of boundless energy, the very foundations of economy and work have been transformed. Traditional currency and material wealth hold little meaning when anyone can access the resources they need with ease. Food, shelter, and basic comforts are provided almost as a given, produced and maintained by automated systems humming with stellar power. People no longer labor for survival. Instead, they choose their pursuits based on passion and curiosity. The question is rarely, what must I do to live? But rather, what shall I do with the life that is fully given? With the end of material scarcity, society's values have shifted profoundly. Achievement is no longer measured by accumulation of goods or energy. Those are effectively infinite. Instead, esteem grows from creativity, knowledge, and contributions to the community. An engineer might spend years designing an elegant solution to a minor problem, not for profit, but for pride in craftsmanship. An artist might construct colossal light sculptures in the sky, visible for miles, purely to share beauty with others. Many people turn inward to refine skills or study the mysteries of the universe simply because they can, and because the pursuit itself gives meaning. Most of the arduous or repetitive tasks of civilization are handled by tireless machines, leaving people free to explore higher aspirations. Farms are tended by autonomous robots. Construction is performed by swarms of self-guided units, assembling buildings molecule by molecule. Even administrative and analytical work can be delegated to advanced artificial intelligences that ensure systems run smoothly. In this landscape, humans have become curators and creators rather than laborers. Their work, if it can still be called work, lies in guiding the direction of progress, tending to the cultural and emotional well-being of the community, and dreaming up new possibilities that machines alone could never imagine. Freed from many dangers and aided by technological marvels, people live longer than ever before. Lifespans easily stretch into centuries, and with advanced rejuvenation, some may choose to live for millennia. This expanded time horizon changes perspectives. Projects that once seemed impossibly long-term are now undertaken as lifetime endeavors. Elders in this society can be hundreds of years old, serving as living libraries of experience and guiding younger generations, not out of authority, but out of accumulated wisdom. Leisure, once a luxury, is now a central feature of life. Lifelong education is common and pursued for its own sake. Universities are filled with students of all ages, delving into subjects from star physics to ancient literature. Arts flourish in every medium. Symphonies play to packed halls at midday. Virtual reality dramas captivate audiences who can step inside stories, and galleries overflow with works crafted from light, sound, and exotic materials conjured by creative minds. Sports and games have also evolved, some taking place in simulated worlds or low-gravity arenas, offering excitement and challenge in a society that no longer struggles for daily survival. Through these endeavors, people find joy, growth, and a sense of achievement divorced from necessity. On any given day, a person may wear many hats. One morning, a citizen might practice on a century-old violin, honing an art that now can be a life's work rather than a hobby stolen between shifts. By afternoon, the same individual might volunteer as a guide in a floating gallery, explaining historical artworks to curious visitors. Come evening, they might join friends in a philosophical discussion under the glow of a sculpted light installation. Work and play blend seamlessly, each undertaking chosen freely. In a society unshackled from want, time itself becomes the most precious resource, and everyone strives to spend it in ways that enrich the spirit. Yet the abundance of everything has brought subtle challenges of its own. In a life without urgent needs or external demands, some people find themselves searching for purpose. Without the push of necessity, motivation must come from within, a reality both liberating and daunting. For many, this means setting personal challenges, climbing an artificial mountain inside a habitat ring, mastering a difficult musical instrument, or embarking on a decades-long scientific research project. Others seek purpose in community, mentoring the young in arts and philosophy, or devoting themselves to exploring the remaining unknowns of science. In the absence of hardship, the act of self-discovery becomes a profound journey, and meaning is something each individual must cultivate. Society in this era of abundance is remarkably cooperative and contemplative. With competition for basic resources obsolete, governance centers on maintaining harmony and fostering personal fulfillment. Decisions are often made through consensus or guided by wise councils whose goal is to balance technological advancement with cultural well-being. Old divisions of nation or creed have softened under the light of a shared sun, leaving people to think of themselves as one community. There's little interest in power for its own sake. Leadership is seen as a temporary service rather than a prize. Crime rooted in desperation has virtually vanished. What remains are only isolated acts born of passion or curiosity, and these are handled with understanding and healing rather than punishment. In general, social life is defined by trust and shared purpose. Everyone recognizes that they prosper together when creativity and kindness form the true currency of their world. A gentle sense of mutual care pervades daily interactions, reinforcing the feeling that this civilization has grown beyond the need for fear or greed. Interestingly, amidst technological perfection, some communities deliberately embrace a simpler life to preserve perspective. In quiet enclaves or floating habitats, groups practice old ways of living, farming with hand tools, crafting goods by hand, even experiencing voluntary power Sabbaths, where they forgo advanced tools for a time. They do not do this out of necessity, but as a form of cultural memory and personal growth. By tasting a bit of the struggle their ancestors knew, they cultivate gratitude for the ease they now enjoy. These pockets of intentional simplicity exist as living museums and spiritual retreats, reminding the wider civilization, not to take its paradise for granted. For all the contentment that suffuses daily life, a gentle undercurrent of introspection runs through society. In quiet moments, some wonder if something essential has been lost in the absence of adversity. Without night, can one truly appreciate day? Without striving, can achievement hold its meaning? Philosophers gather in sunny courtyards to debate such questions, acknowledging that humanity has stepped into a godlike realm of abundance and power. Their consensus is hopeful but cautious. This civilization must continually seek purpose and wisdom to match its technical might. After all, holding the reins of a star confers great responsibility, and they know that hubris could yet cast a shadow, even in a world of endless light. Living with a star as one's hearth has left an indelible mark on the human psyche. There is a deep sense of awe at what has been accomplished. At times, a person looking upon the endless light feels almost godlike, a master of nature's power. Yet in the very next breath, that same individual might be struck by profound humility, realizing that they are a tiny being orbiting a sun, even if that sun is now enclosed in their creation. The contrast between the seeming omnipotence of harnessing a star and the enduring mystery of the cosmos creates an undercurrent of tension in the mind. Have they become mighty creators, or are they still children playing with forces beyond full understanding? From time to time, conversations turn to the ancient warnings of hubris. Humanity's folklore and history are rich with tales of those who reached too far. They remember Icarus, who flew on crafted wings and fell when he ventured too close to the sun, and Prometheus, who was punished for stealing the god's fire. In these myths, people of the Dyson sphere see echoes of their own story. They have, in a sense, taken the fire of the sun entirely for themselves. So, quietly and collectively, they remind one another to remain humble. They hold ceremonies on occasion, moments of reflection under an artificially dimmed sky, to acknowledge that what they have built is extraordinary and fragile, and that respect for the forces of the universe must never be lost. Beneath the surface of daily contentment, there is also a subtle fear, an awareness that their lives depend on a vast construct and the steady grace of a star. Parents sometimes wake from dreams in the long daylight, hearts pounding, imagining the sphere cracking or the sun erupting in an uncontrollable flare. Psychologists counsel those who develop anxieties about the shell, as they call it, a lingering worry that the very structure protecting and nourishing them could, in some unforeseen calamity, become a prison or a weapon of their undoing. These fears are rarely spoken aloud in the brightness of day, but they exist in private thoughts and diaries kept during artificially dim hours of repose. Such undercurrents ensure that even in a world of constant light, shadows of doubt persist. In response to these anxieties, new philosophies and spiritual perspectives have blossomed. Some people have come to regard the captured sun not merely as a tool, but as a partner in existence, a kind of cosmic being that must be honored. They form gentle cults of gratitude, gathering to sing hymns to the sun at designated hours when cities dim their lights. Others, perhaps more secular, preach the philosophy of the steady hand, the idea that it is humanity's duty to wield this immense power wisely and compassionately, to become caretakers of the star rather than its conquerors. Across the sphere, whether in meditative retreats or scholarly debates, a common thread is the quest to ensure that moral growth keeps pace with technological might. It is telling that even in a civilization of unending day, people still seek out darkness from time to time. There are darkened sanctuaries built deep within the sphere's habitable ring, quiet places where one can sit under a simulated night sky. In these observatories, The far-off pinpricks of real stars outside are projected or revealed through small apertures in the shell. Visitors come here to gaze upward and remember the infinite cosmos beyond their creation. In the tranquil dark, they often report feeling a comforting smallness, a reassurance that though their own power is vast, they are still part of a greater universe. These pilgrimages into darkness act as a counterbalance, grounding the soul so it does not float away on excess pride. One such visitor, an old poet whose life spans centuries, stands in a darkness-draped dome with eyes full of tears as he beholds the Milky Way. He whispers an ancient verse about the humility of starlight, lines passed down through generations. For him, and for others like him, these moments are a dialogue with the universe, a pledge that despite enclosing a sun in metal and mirror, they have not sealed themselves off from wonder. In the poet's voice is gratitude and a hint of apology, as if speaking to the stars. We have taken this bold step, but we have not forgotten our place among you. There are thinkers who worry about the spirit of humanity in an age where nearly all wants can be satisfied. They ask, does a life without hardship make us weaker in character, less creative, perhaps less compassionate? These philosophers sometimes argue for the importance of self-imposed challenges and of cultivating empathy through memory of past struggles. They champion the idea that adversity, even if now rare, must not be completely purged from life's story, that some of the greatest human virtues were born from overcoming difficulties. In the halls of great universities and in quiet forums, people earnestly discuss how to keep the edge of inspiration sharp and the depths of empathy deep, lest comfort alone lull them into a shallow contentment. Thus, under the perpetual noon of their own making, the denizens of this stellar civilization walk a line between exaltation and caution. They celebrate what they have achieved, a life free of many ancient woes, but they also carry the wisdom of restraint in their hearts. Every festival of light is tempered with a silent prayer of thanks and a promise not to let arrogance grow unchecked. They know that the same ingenuity that gave them the stars could, if misused, lead to downfall. Balancing pride and humility, power and conscience has become a central part of their culture. In nurturing this balance, they hope to ensure that their reign around the sun remains benevolent and enduring. The masters of this stellar habitat have learned that true mastery lies not in domination, but in balance. In the early days after the sphere's completion, there were temptations to micromanage every aspect of the environment, to sculpt every inch of land and program every breeze. But over time, wisdom prevailed. They discovered that life thrives best when given gentle guidance rather than absolute control. Gradually, they adopted a philosophy of partnership with their technologies and their environment. A core principle emerged: intervene lightly and listen to what nature needs. The systems that run the Dyson sphere work in concert with natural processes, nudging here, adjusting there, but also letting forests grow wild and seas follow their ancient rhythms. This equilibrium did not emerge overnight. It was the result of attentive stewardship and humility before the complexity of living systems. Every innovation introduced into the sphere is measured against its impact on the whole. New power devices or habitat modules are first tested in careful simulations to ensure they harmonize with existing ecosystems. If a particular technology threatens to upset the thermal balance or the atmospheric composition, it is redesigned until it is gentle on the world. Engineers and ecologists work side by side, blending circuitry with soil and algorithms, with sunlight as co-architects of the environment. The result is a realm where technology exists almost invisibly within the tapestry of nature. Solar collectors double as leafy canopies, and climate controls mimic the subtle shifts of natural weather patterns. In achieving this unity, the civilization has truly become the gardener of an entire world. It prunes and nurtures, but never strangles the life it oversees. With an eye on eternity, they plan for the future of both star and society. The Dyson sphere is built to last for millennia, and its keepers maintain it with the utmost care, routinely repairing and upgrading its components, using resources recycled in endless loops. They have calculated the star's life cycle and put in place strategies for far-off times, how to adjust as the sun slowly changes, how to perhaps one day ignite new stars or migrate to them when this one grows old. This long foresight permeates their culture. Decisions are made not just for the next year or generation, but for centuries and eons ahead. In this way, control is exercised with patience and prudence, always keeping in mind that their stewardship of the star must serve generations yet unborn. One might expect that with near infinite energy, the civilization would expand without limit, but they have consciously chosen a path of moderation. Population growth is balanced and carefully managed so that communities can flourish without straining even the vast capacity of the sphere. People live widely and comfortably, but they avoid overcrowding by design, preserving plenty of open spaces for nature and solitude. This ensures that even in a world of abundance, there is room to breathe and a sense of harmony. Material consumption, too, is approached with restraint and artistry rather than wanton excess. Goods are built to last and carry personal meaning rather than to be used briefly and discarded. The citizens remember the cautionary tales from their history of societies that once damaged their planets through careless exploitation. Unlimited power has taught them that having great abundance does not mean one must indulge in it without thought. Instead, using resources wisely has become a point of pride, a sign of maturity that ensures their abundance remains a blessing and not a curse. A key element of this harmony is the relationship between human and machine intelligence. Advanced AIs monitor the star's output, climate patterns, and infrastructure health, making adjustments faster than any human could. But these AIs are not the overlords of the sphere. They function as extensions of human intent and ethics. Regular councils review the algorithms that guide the world, ensuring they align with the values of life and balance. This transparency and cooperation prevent technology from becoming a runaway force. Instead, it remains a trusted guardian. People often speak of the sphere itself as a living system, one in which synthetic minds and organic minds are partners in keeping the heart of the sun steady and the soul of society healthy. At dawn, or what is called dawn when the light panels slowly brighten, one can stand at the edge of a vast bioengineered wetland and watch a gentle mist rising from the waters. In the distance, mirrored towers glint softly, their orientations shifting to direct just the right amount of sunlight to the wetland for the morning. Birds take flight across a sky that is both natural and designed, and beneath the surface, sensors quietly track water quality to keep it pristine. A poet observing this scene notes that it's impossible to tell where nature ends and human craft begins, and that is by design. The highest praise in this society is that something built by human hands appears as elegant and life-giving as if nature itself had made it. This harmony is not a static achievement, but a dynamic practice. The people of the sphere remain vigilant, knowing that balance can be lost through complacency. They continuously study their environment and themselves, ready to adapt if a new factor, perhaps an unexpected behavior of the star or a subtle ecological shift, arises. When minor imbalances occur, they treat them as gentle lessons rather than crises. A slight increase in atmospheric temperature leads to a collaborative project between scientists and artists to plant new shade flora and adjust mirror angles, cooling the region in a way that also creates beautiful shifting patterns of light. Every challenge is met with creativity and calm, reinforcing the resilience of their controlled yet organic world. Through these ongoing efforts, the civilization has refined a philosophy often spoken of simply as the balance. It is the understanding that controlling a star and a world is an ethical art as much as an engineering feat. In this balance, technology serves biology, and progress is paced by conscience. Children in this society are raised with stories of how the sphere itself listens, how every action, every invention must sing in harmony with the grand orchestra of life humming under the dome. This cultural ethos ensures that as knowledge grows and capabilities expand, the guiding principle remains. First, do no harm to the symphony that sustains them. Standing on a high terrace at the sphere's inner edge, one can gaze across continents illuminated by engineered daylight and feel a profound sense of peace. The star at the center blazes steadily, its power channeled but not abused, its gift nourishing every endeavor. The humans of this age have come to understand that their greatest strength lies not in what they can take from their sun, but in how gently they can hold it. This delicate relationship, hand in hand with a star, defines their civilization. It promises a future in which they not only survive and prosper, but perhaps even evolve into wiser beings under the tutelage of the very light that gave them life. Yet even as they achieve this remarkable equilibrium, they know the story is not over. The cosmos beyond the sphere still calls to them in silent ways. Distant stars, unanswered questions, and possibilities, yet unimagined. In their harmony, they find the strength and clarity to look outward without fear. The civilization of light is prepared, in time, to spread its wisdom to new frontiers, or to welcome whatever unknown wonders might one day find them. The journey of life around this captured star continues, ever evolving, ever hopeful, a testament to what can be when great power is guided by great care. In the darkness of space, most stars announce themselves with bright starlight. But imagine a star that no longer shines visibly, a hidden sun wrapped in a colossal shell. To our eyes, it might appear nearly dark, yet it would not be truly silent. Enclosed in that megastructure, the star's energy would still seep out as heat. This faint warmth, glowing in infrared wavelengths, would be like a whispered secret in the void. Long before we had the means to search the skies in infrared, scientists speculated about this possibility. Decades ago, physicist Freeman Dyson proposed that if extraterrestrial civilizations built such megastructures around their stars, those stars could be found not by their light, but by their heat. In a sense, he suggested we look for stars that were oddly cool for their usual brightness, or unusually bright in infrared for their type. Anomalies that might signify a star's light being captured and re-emitted as lower energy glow. This idea turned the search for alien life on its head. Instead of listening for messages, Dyson advocated hunting for the quiet thermal footprints of giant engineering projects. As technology advanced, astronomers took up that challenge. We began to survey the sky with infrared telescopes, eyes that could see warmth across the light years. Every object with a temperature gives off some infrared glow, from the heat of a planet's atmosphere to the warmth of interstellar dust clouds. Amid this natural infrared background, a Dyson sphere would stand out as a peculiar kind of object. Essentially a warm, dark sphere, roughly the size of a planetary orbit. For example, if a star like our Sun were enclosed in a Dyson sphere, the structure might be heated to a few hundred degrees by the star within, making it glow in infrared wavelengths. From Earth, we wouldn't see the star's usual twinkle of visible light. Instead, we might notice an unexpected ball of heat, something too warm and too large to be a simple cool star, yet not bright to optical telescopes. This infrared telltale has been poetically called the infrared whisper of a hidden sun. It's an evocative image, a star essentially muffled, its brilliant light quieted to a soft murmur of warmth leaking through its shroud. Detecting such a whisper is a delicate task. Our instruments must be sensitive enough to pick out a slight excess of infrared radiation that doesn't fit a normal stellar profile. It is like trying to detect a faint ember in a gusty night, easy to overlook unless you search carefully and know exactly what to look for. Early infrared sky surveys, starting in the late 20th century, were the first attempts to scout for these hidden embers. Astronomers combed through catalogues of infrared sources, looking for any that had peculiar properties. Perhaps a star that seemed unusually dim in visible light, but brighter than expected in infrared. If we found one, it would serve as a clue worth investigating. There was a thrill in this prospect. Could a simple, all-sky infrared map harbour evidence of cosmic engineering? It was a bold and imaginative hope. And while those early surveys did not unveil a clear-cut Dyson sphere, they laid the groundwork for more refined searches in the future. Over time, the hunt has grown more sophisticated. Scientists have developed dedicated programs to search not just our local neighborhood, but even across the Milky Way, for the waste heat of advanced civilizations. If a civilization were ambitious enough to enshroud even a fraction of a star, the energy it collects would inevitably leak away as heat. Energy on the scale of a star is immense. No matter how efficient or secretive the project, the waste heat would be prodigious. It's like trying to hide a bonfire behind a curtain. Some warmth will always glow through. Modern surveys now use space-based infrared observatories, scanning millions of stars systematically for that faint warm excess that might signal an artificial shell. Now and then, a star with an odd infrared glow does emerge from the data. Each time, it triggers intense scrutiny. Could this finally be the sign of a distant megastructure? Usually, the answer turns out to be more mundane. A cloud of dust around the star, or even a distant dusty galaxy aligned by chance in the same direction, masquerading as something mysterious. Each such case, though initially disappointing, helps astronomers refine their methods. We learn how to better distinguish the ordinary from the extraordinary, sharpening our eyes for the next search. Even so, the principle remains sound. If a Dyson sphere exists out there, its star cannot hide completely. The laws of physics ensure that energy harvested must be radiated away again as heat. Thus, a star's stolen light would reappear as a telltale thermal glow. This is the silent signature we seek. Not a flashing beacon of radio or laser, but a subtle infrared hum against the cold backdrop of space. It is a gentle clue, one that demands patience and precision to detect. Like listening for a whisper in a storm, we must filter out the roar of natural cosmic processes to catch the quiet hint of an alien engineering marvel. Today, the idea of searching for such infrared traces is an accepted part of the broader quest to find extraterrestrial intelligence. Alongside listening for radio signals or scanning for chemical biosignatures, scientists keep this heat-hunting strategy in their toolkit. It's a strategy that doesn't assume aliens are trying to talk to us. It simply assumes that if they build enormous structures, physics will broadcast their presence in some form. In a universe that has offered no direct greetings, looking for a thermal footprint is a way to let advanced beings reveal themselves by their works rather than their words. If they are out there constructing grand megastructures around stars, they might be leaving fingerprints in the form of excess infrared radiation, just waiting for a keen observer to pick up. And so, in the quiet streams of data pouring down from our infrared telescopes, astronomers continue to watch and hope. Each star's spectrum is checked for subtle anomalies. Most potential hints so far have turned out to be dust, or quirky stars, or distant galaxies masquerading as something strange. But the search goes on, methodically and relentlessly, like a cosmic game of hide-and-seek played out over years and light years. The question is simple and profound. Could one of those countless points of starlight in the night sky be something more? A beacon of an unimaginably advanced civilization? A hidden sun cloaked by design? If so, finding it would be among the most significant discoveries in human history. And so we scan the darkness for that faint, warm whisper, listening with open minds, hoping that somewhere a hidden sun might whisper back and tell us we are not alone. If an advanced species began assembling a Dyson swarm around its sun, an outside observer might notice that star flickering strangely. As panels or structures accumulate in orbit, the star's light could dim at irregular intervals and by unusual amounts. To astronomers, it would look like a mystery, a normally steady star that suddenly drops in brightness in erratic ways. This idea isn't just theoretical. In recent years, we've actually observed a star that behaves a bit like this, and it made us wonder if we were witnessing something extraordinary. In 2015, a star about 1,500 light-years from Earth became the focus of intense curiosity for exactly this reason. Catalogued as KYC 8462852, it's better known now as Tabby's star, named after astronomer Tabitha Boyajian, who studied it. Data from NASA's Kepler Space Telescope revealed that this otherwise ordinary star was dimming in ways we had never seen before. At one point, it lost nearly 20% of its brightness, an immense dip. And it did so not in a regular, periodic way, like a planet might cause, but unpredictably. For comparison, a Jupiter-sized planet transiting a sun-like star causes only about 1% dip in light. A 20% drop suggested something far larger or more complex than a planet was blocking the starlight. These strange observations set off a flurry of speculation and excitement. Some in the media dubbed KYC 8462852 the alien megastructure star, wondering aloud if we might be seeing a Dyson swarm under construction. Could it be that large, irregularly shaped objects, perhaps colossal solar collectors or habitats, were intermittently eclipsing the star? It was a wild hypothesis, and scientists themselves were cautious. Extraordinary claims demand extraordinary evidence, and there were plenty of natural possibilities to consider first. Nonetheless, the public imagination was captured by the idea that we might finally have spotted evidence of an advanced civilization at work. Over the next few years, astronomers around the world observed Tabby's star with every instrument they could, from ground-based telescopes to orbiting observatories. They looked at it in different colours of light, trying to puzzle out what could be causing the dimming. If opaque megastructures were blocking the star, the dimming should affect all wavelengths of light roughly equally. But if translucent dust were responsible, blue light would be dimmed more than red light, because fine dust grains scatter shorter wavelengths more strongly. The data ultimately showed that Tabby's star's dips were indeed wavelength dependent. The star faded more in ultraviolet light than in the infrared. This was a strong clue that ordinary dust, not alien technology, was the culprit. Moreover, Infrared observations didn't find the excess glow that a swarm of solid objects might produce. Bit by bit, an explanation involving natural phenomena came together. The prevailing theory that emerged was that Tabby's star is surrounded by an irregular cloud of dust or debris. Perhaps a family of comets was disrupted, creating a swarm of fragments that occasionally block the star's light. Or maybe an orphaned exomoon, a moon freed from its planet, was shattered, and its dusty remnants now orbit in clumps. These scenarios could produce large, uneven dimmings without leaving a clear infrared signature. By 2018, studies pointed strongly to dust as the reason for the star's weird behavior. The alien megastructure idea, while thrilling, was set aside by evidence that did not require intelligent intervention. Yet Tabby's star remains a fascinating case. It taught us that even in our own backyard of the galaxy, there are stars doing things we didn't expect and still don't fully understand. It reminded us not to jump straight to aliens when confronted with an anomaly. Nature often has many surprises up her sleeve. At the same time, it showed that it's possible to detect extremely subtle and strange fluctuations in starlight. If a partial Dyson swarm were ever in progress somewhere, our telescopes and algorithms might catch something like it. The case of Tabby's star served as both a caution and an inspiration. Caution that extraordinary claims require rigorous proof, and inspiration that mysteries still abound in the sky, waiting for curious minds to unravel them. While Tabby's star turned out not to be proof of ET, it galvanized the scientific community to launch more systematic searches for dimming suns. Astronomers have since combed through Kepler's database of hundreds of thousands of stars, looking for others that flicker or fade in odd ways. A few candidates with unusual light curves have been found, though most can be explained by natural causes like variable stars or eclipsing dust clouds in young stellar systems. None so far has the same level of intrigue as Tabby's star did initially. But the important thing is that we are now actively looking. Every unexplained dip or strange cycle in a star's brightness gets scrutinized carefully. Advanced algorithms and even citizen scientists, as was the case with Tabby's discovery, scour the mountains of telescope data for patterns that don't match ordinary stars or simple planet transits. This vigilance means that if any star in our surveys starts behaving in a truly unexplainable way, we'll likely catch it. It could be a fluke of nature, another cosmic oddity to investigate, but one can't help keeping that tiny possibility in mind. Perhaps, just maybe, it could be something engineered. We know now to follow the evidence and not let our imaginations race ahead of the data. Still, the dream persists that one day we might stumble upon a star that dims not because of dust or comets or internal hiccups, but because someone out there is building something immense. The idea that alien megastructures might reveal themselves through irregular starlight is no longer fringe science. It's a topic taken seriously, in part thanks to cases like Tabby's star. The lesson learned is to remain both open-minded and skeptical. We must be ready to consider extraordinary explanations, but only after ordinary ones have been exhausted. And if the day ever comes when all natural explanations fail for a particular signal or observation, then perhaps we will allow ourselves the extraordinary conclusion that we have detected the work of intelligence across the gulf of space. Until then, we continue to watch the stars for any strange flickers, knowing that even in their quiet, they have stories to tell. Stories of planets, of dust clouds, of things we understand, and things we have yet to understand. One of those stories might, one day, be the story of someone else out there, reaching across the light years, even if unwittingly, to announce their existence through the silent language of starlight. With modern instruments and ambitious surveys, the hunt for alien megastructures has become more than a speculative musing. It's a scientific endeavor. In recent years, astronomers have harnessed powerful observatories to scan the skies for those subtle clues. NASA's Kepler Space Telescope, for instance, gave us the ability to monitor the brightness of over 150,000 stars continuously for years. While its primary mission was to find exoplanets, it incidentally provided exactly the kind of data one would need to spot a Dyson-like obscuration: precise, long-term light curves of distant suns. Kepler's trove of observations has been combed not just for the tiny, regular dips of orbiting planets, but also for the odd, irregular plunges that might hint at something extraordinary. That's how Tabby's star was found, by diligent analysis, including by citizen scientists, of the Kepler data, searching for anything that didn't match the usual pattern. Today, other missions have taken up the mantle. NASA's TESS, Transiting Exoplanet Survey Satellite, now scans nearly the entire sky, sector by sector, catching periodic flickers of planets passing in front of bright nearby stars. TESS's gaze isn't as constant on one spot as Kepler's was, but it covers a vastly larger number of stars over time. Along with finding hundreds of new exoplanets, TESS provides light curves that could reveal unusual stellar behavior. Scientists keep an eye out for any TESS target that dims strangely or inconsistently. Even if TESS only watches a given star for a month or so, its data could flag an anomaly that bigger telescopes can then follow up on for longer periods. In parallel, infrared surveys have continued to expand. The all-sky mapping done by the WISE satellite, Wide Field Infrared Survey Explorer, and its successor missions has given us catalogues of literally billions of infrared sources. Researchers have written algorithms to comb through these databases to find stars that are too bright in infrared for their type, or unexpectedly faint in visible light for their measured infrared glow. By cross-referencing data from WISE, from the Gaia mission, which provides distances and intrinsic brightness for stars, and from other surveys, teams have drawn up lists of potential Dyson sphere candidates. These are objects that, on paper, have the sort of mismatched energy output one might expect if some of their starlight were being absorbed and re-radiated as heat. When a list of such candidates is created, the real work begins. Astronomers point more specialized instruments at them. For instance, the powerful new James Webb Space Telescope, JWST, can take detailed spectra in the infrared. If one of these stars truly had a partial Dyson sphere, JWST might detect a telltale signature: an excess of infrared radiation following a very specific curve that corresponds to a near uniform temperature, the temperature of the Dyson structure, absorbing and re-emitting the star's light. In 2024, one team announced they had found a handful of intriguing stars using WISE and Gaia data. Small red stars that were unexpectedly warm in infrared. Excitement bubbled that these could be real examples of engineered structures. But follow-up analysis, including careful checks for contamination by background galaxies, suggested more mundane explanations. In fact, those stars likely had dusty disks, or were aligned with distant, infrared bright galaxies, so-called hot dogs, hot dust-obscured galaxies that confused the data. The initial thrill subsided, but the process was a success in terms of methodology. The search criteria worked, candidates were found, and then thorough follow-ups were done to rule out false positives. This is how the search with modern eyes proceeds, systematically, cautiously, but always pushing outward. We use space telescopes like JWST to peer into promising systems with unprecedented clarity. We rely on missions like Gaia to provide a precise cosmic census against which we can spot the oddities. we plan for future observatories. Perhaps one day, a dedicated infrared interferometer in space could directly image the glow of something like a Dyson sphere, or the Vera C. Rubin Observatory on Earth, with its all-sky nightly survey, might catch a star that slowly fades over years, as if being enclosed. Each new tool is another set of eyes, watching the universe for a flicker or a glimmer that says, someone is here. It's worth noting that our searches aren't confined to the Milky Way. Ambitious astronomers have even examined other galaxies for unusual properties. A truly advanced civilization, one a step beyond Dyson spheres, perhaps a Kardashev Type 3 civilization, might modify the energy output of an entire galaxy. In theory, if a galaxy's light was significantly shifted toward the infrared, as if many of its stars were cloaked, it would stand out in our surveys of galaxies. Studies of hundreds of thousands of galaxies observed by WISE looked for this, but none were found that couldn't be explained by natural astrophysics, such as galaxies rich in dust and new stars. While it might have been awe-inspiring to discover a galaxy-wide civilization, the lack of such obvious examples mostly tells us that if Type 3 civilizations exist, they are either extremely rare or very good at blending in. That aligns with the general finding of our searches so far. No unmistakable techno-signatures anywhere in the vast sky, at least not yet. Still, the absence of evidence is not evidence of absence. Our modern eyes have only begun to gaze upon the cosmic ocean with the sensitivity required to see subtle signs of life and intelligence. There is a quiet confidence among researchers that if such things are out there within a reasonable distance, we have a chance of noticing them now or in the near future. Each improvement, every larger telescope mirror, every new detector that can see a bit further into the infrared, every algorithm that can filter out noise a little better, increases the odds. We cannot say when or even if a discovery will come, but we can say that we are better equipped than ever before. For the first time in human history, we have the capability to detect the faint heat of an alien megastructure, or the odd wink of an engineered eclipse, should they exist. The sky has been surveyed and catalogued in depth. The haystack has been mapped, and now we are carefully searching it for any needle that glints oddly against the cosmic hay. As the data pour in and the analyses churn on, one cannot help but wonder, if advanced civilizations are out there, why haven't we found any clear trace yet? This returns us to Fermi's nagging question and sets the stage for deeper reflection. Our searches with modern eyes have, in effect, confronted us with the possibility that maybe the cosmos really is devoid of other builders, or at least so rare that we might never bump into them. That realization can be disheartening or empowering, depending on one's perspective. In the next part of our journey, we'll grapple directly with this existential question. If Dyson spheres are possible, where is everybody? And what does it mean for us if the answer is nowhere within sight? Our sharpened vision of the stars has given us unprecedented knowledge, but also a new sense of solitude, a paradox that invites both awe and introspection as we move forward. The apparent absence of alien megastructures leads us back to a profound question famously posed by Enrico Fermi. Where is everybody? If technologically advanced civilizations are common in our galaxy, shouldn't some evidence of them be obvious by now? A signal, a probe, or perhaps the telltale glow of a Dyson sphere cloaking a distant sun. This conundrum, known as the Fermi paradox, hangs over our observations like a challenging riddle. We have billions of stars and potentially countless planets, many far older than Earth, which suggests ample opportunity for life and intelligence to arise. Yet as we scan the skies, we see no unmistakable sign of cosmic company. The silence, in light of what our theories predict, is difficult to reconcile. One straightforward resolution to the paradox is that advanced civilizations are exceedingly rare, perhaps so rare that we might indeed be alone in the Milky Way, or at least the first such civilization to arise in our corner of the cosmos. This notion, sometimes called the rare Earth hypothesis, paints a sobering picture of cosmic loneliness. It could be that life itself is incredibly scarce, or that the step from simple microbes to intelligent, technological life is astronomically unlikely. Under this view, the reason we don't see Dyson spheres is simply because no one else has ever gotten to that level. The night sky remains natural and unchanged because we are the only ones, or among the very few, who have ever dreamed of engineering stars. In a galaxy of billions of worlds, our civilization could be a solitary beacon, which may be why nothing else has signaled back. It's a possibility we have to acknowledge, as disquieting as it may be. Another possibility is that life, and even intelligence, may be common. But the leap to building star-spanning megastructures is not. Civilizations might exist in many places, yet never reach the ambitious heights of Dyson sphere construction. Perhaps they self-destruct before they get there, wiping themselves out through war, environmental collapse, or other catastrophes, a concept known ominously as the Great Filter. Some thinkers speculate that this Great Filter is a hurdle that almost no civilization manages to overcome. It could be behind us. Maybe the transition to multicellular life or the evolution of intelligence is incredibly rare. Or ahead of us. Perhaps technological societies inevitably trigger their own demise. In this scenario, many civilizations could light up briefly like fireflies on a summer night, only to extinguish before we ever notice them. None survive long enough, or grow bold enough to start wrapping stars in shells. But let's suppose some civilizations do endure and progress. Why might they still refrain from or avoid building Dyson spheres? One intriguing answer lies in reconsidering the assumption that exponential growth and ever-increasing energy use is inevitable. Maybe truly wise species learn to live in balance with their environment and find sustainable ways to thrive without gargantuan engineering. They might achieve a form of equilibrium, harnessing enough energy for a comfortable existence, but not indulging in the cosmic extravagance of stellar engineering. In fact, some researchers have proposed a sustainability solution to the Fermi paradox. It argues that no civilization will ever use all the energy of its planet, star, or galaxy, because such growth is unsustainable or simply not desirable. Under this philosophy, the hallmark of advanced intelligence could be self-restraint rather than expansion. No wonder we don't see Dyson spheres. Perhaps no one is actually trying to build them, as it's not seen as a prudent path by those civilizations. There's also the possibility that advanced beings choose pathways we can barely imagine. Paths that don't leave obvious visible traces. Consider a civilization that turns inward, pouring its ingenuity into virtual realities or digital realms, requiring minimal physical infrastructure. Such a society might steadily reduce its cosmic footprint, focusing on knowledge and simulation more than raw energy. They could effectively fade out from the observable universe, becoming quiet and small in external appearance, not because they perished, but because they transcended the need for conspicuous physical structures. Our telescopes would see their star systems as normal and untouched, because their grand works are happening in miniature scales or in dimensions of thought we have no means to detect. In a sense, they might ascend to modes of existence that render them invisible to our searches for things like Dyson spheres. Then there is the darker conjecture that advanced civilizations actively hide. Perhaps they've learned that broadcasting one's presence, via loud radio signals or galaxy-scale engineering, is a recipe for disaster. In the cosmic jungle, the argument goes, the safest strategy is to be quiet and camouflaged. In this dark forest scenario, every civilization conceals itself out of fear that others might be hostile. A species capable of building a Dyson sphere might equally be capable of disguising it, blending its waste heat into the cosmic background, or engineering a faux signature that looks natural. Even here on Earth, some scientists have debated whether it's wise for us to shout our existence to the cosmos, lest we draw unwanted attention. If the aliens share that caution, our searches would turn up empty, not because no one is out there, but because they are deliberately staying inconspicuous. It's a chilling thought. The quiet cosmos might be like a dark forest at night, full of life hiding behind the trees, each fearful of making the first sound. And yet, we cannot ignore the contrary possibility that we haven't found them simply because we haven't looked long enough or hard enough. Our search efforts, while growing, have still examined only a tiny fraction of the galaxy, with the sensitivity required to find subtle techno-signatures. Dyson spheres might be exceedingly uncommon, but perhaps not non-existent, and it could take more time and better instruments to stumble upon the right evidence. After all, it's a vast galaxy. If only one star in a million hosts a Type 2 civilization, that would still mean potentially hundreds of such systems in the Milky Way. But finding those among billions of stars is a Herculean task, akin to finding a handful of needles in an enormous haystack. Many sections of the sky and many wavelength bands remain underexplored. It's possible our current surveys simply haven't yet had the reach or resolution to catch those rare outliers, or that the first Dyson sphere is just a bit beyond our present horizon. Interestingly, our searches have not been limited to individual stars. Scientists have also looked for signs of even more extreme cosmic engineering. In the 1960s, astronomer Nikolai Kardashev proposed a scale for classifying civilizations by energy use. A Type 1 civilization harnesses the resources of its home planet. Type 2 harnesses the energy of its star. A Dyson sphere would fall in this category. And a Type 3 harnesses the power of an entire galaxy. If civilizations far more advanced than we can imagine, Kardashev's Type 3, were harvesting energy on the scale of whole galaxies, we might detect their presence by the way those galaxies shine. A galaxy full of stars partly cloaked by Dyson swarms would emit a strangely high amount of infrared radiation relative to its visible light. A few years ago, astronomers scanned hundreds of galaxies to see if any were too warm in this way, emitting more infrared than they should. They did identify some oddball galaxies, but those turned out to have natural explanations, like enormous dust clouds and frenzied bursts of star formation, rather than the fingerprints of galactic-scale life. Just as we have not found unmistakable Dyson spheres in our neighborhood, we haven't spotted any galaxies that scream engineered by intelligence. If great cosmic empires exist, they either are extremely well hidden or absent in the regions we've surveyed. The lack of evidence thus far leaves us with more questions than answers. It forces us to confront our own assumptions about life and intelligence. Were we perhaps naive to imagine that alien civilizations would inevitably reveal themselves through giant constructions or signals? It might be that our idea of technological progress is deeply rooted in our own human experience and not a universal template. Maybe many intelligent species find contentment in ways that leave no mark on the stars, or develop technologies indiscernible to us. The cosmic silence challenges us to stay humble and keep an open mind. Either we truly are alone in our ambitious reach, or the others out there are doing things we haven't yet conceived of, or, just maybe, quietly observing us without our knowing. Enrico Fermi's simple question still echoes without an answer. For now, each silence from our telescopes, each empty patch of sky where we hope to see a Dyson sphere or hear a signal, nudges us toward the sobering possibility that advanced life is exceedingly scarce. But science thrives on the possibility of surprise, and all it would take is one discovery, one indisputable sign of alien engineering or communication, to transform our understanding in an instant. Until such evidence appears, we dwell in a paradox. On theoretical grounds, we feel we ought not to be alone. Yet observationally, we cannot escape the impression that we are. It's a conflict between our expectation and our reality. And it keeps the discussion of where is everybody very much alive. This tension between expectation and reality keeps the Fermi paradox a topic of lively debate. Each proposed solution, from the idea of a great filter to the notion of a cosmic zoo or simulation, offers a very different picture of our place in the cosmos. As our searches continue to improve, we may eventually tilt the scales one way or the other. We might end up finding nothing concrete, which would strengthen the argument that something inherently limits the emergence or expansion of intelligence. Or, with a stroke of luck, we could find a Dyson sphere or receive a clear signal that answers Fermi's question at last. Imagine that moment, the quiet broken by confirmation that we are not alone. It would mean that building such megastructures is not just a theoretical possibility, but a reality for someone out there. In the meantime, the silence teaches us both patience and a sense of responsibility. It reminds us that even grand ideas like the Dyson sphere, so tantalizing in theory, might be rarer in practice than we assumed. Or if they exist, they remain just beyond our current grasp. Perhaps, if the cosmos truly holds its breath with no other voices, the duty falls to us to ensure that life and intelligence continue to flourish. If we are the only technological civilization in this galaxy right now, that makes our actions and choices monumentally significant. It means we carry the flame of awareness alone through the cosmic dark. That perspective can be sobering, but also empowering. So we continue to look up and listen, grappling with the cosmic silence and what it means for our future. In that silence lies a challenge and an inspiration. If someday we detect the faint glimmer of a Dyson sphere, or hear a distant whisper from the stars, we will finally know that others share this universe with us. And if instead we remain the sole voice we can hear, then perhaps we are destined to become the pioneers, the ones to light a beacon around our own sun, to do what no one else has done yet. But whether we find a neighbor or become the first, one thing is certain. The moment of discovery, either way, will come with profound responsibilities and ethical questions. How should we greet another civilization? Or how should we conduct ourselves as we step onto the cosmic stage? These questions lead us to consider the ethics of discovery, what it would mean to find or to be found. How would we react if tomorrow our telescopes confirmed an alien Dyson sphere around a distant star? The question is not just scientific, it's deeply ethical and philosophical. Such a discovery would be exhilarating, but it would also confront us with choices that could shape humanity's future. We would suddenly know we are not alone, and that realization would challenge our beliefs, our philosophies, and our sense of place in the universe. For starters, there's the issue of communication. Do we attempt to reach out to this far-off civilization and say hello, or do we remain silent observers? At present, the general consensus among SETI scientists is caution. If we detect evidence of extraterrestrial intelligence, the first step should be to verify it and then openly inform the world. No secret dealings or unilateral actions. But after that, whether to send a reply is an open question. with passionate voices on both sides. Some argue that if we find clear evidence of others, we have a duty to reach out in friendship. As fellow intelligent beings, how could we not at least try to communicate? Others, however, urge restraint. They point out that we know nothing about the civilization that built the Dyson sphere, neither their intentions nor their dispositions, and that by broadcasting our presence, we could be taking a tremendous risk. This conflict, the desire to connect versus the instinct for self-preservation, has no easy resolution yet. We can't help but recall our own history as we weigh these options. When technologically advanced cultures on Earth encountered others who were less advanced, the results were often painful or even catastrophic for the latter. That memory casts a long shadow over our hopes. If a civilization is advanced enough to build a Dyson sphere, they would be far beyond us in power. Would they be benevolent teachers, indifferent observers, or something far more threatening? The truth is, we have no way to know, and that uncertainty makes many rightly cautious about shouting our presence from the rooftops of Earth. Beyond the question of danger, there is the question of our own readiness. Are we, as a global society, prepared emotionally and politically to handle the knowledge of another civilization? Some experts believe that even confirming a distant megastructure would profoundly affect our worldviews and possibly our social stability. It could unite us, making us see all humans as one group in contrast to them, or it could spark anxiety and division, depending on how the news is handled. We might also ask, who gets to represent Earth if actual communication becomes possible? Right now, there is no single global authority designated to speak on humanity's behalf, and that could lead to confusion or conflict if we're not proactive in thinking about it. Imagine instead that the roles are reversed, that one day we are the ones being contacted or even visited. If an alien civilization finds us before we find them, the ethical burden shifts. We would hope they approach us with patience and respect, but we cannot guarantee it. How should we respond if a message from an advanced society suddenly blares through our radio telescopes, or if a spacecraft appears in our skies? Humanity would have to make quick yet weighty decisions. Many have suggested developing a first contact protocol for such an event, laying out steps for communication and safety. The underlying principle would likely be to show courtesy and caution, answer questions truthfully, avoid provocation, and ensure that no single faction of humanity speaks or acts for all without consensus. Encountering another civilization also forces us to consider how we present ourselves and what we ask for. Would we, for instance, immediately beg them for advanced technology to solve our problems? That could be tempting, but ethically, it raises issues of dependency and cultural upheaval. It might not be wise or right to leapfrog our own development by using alien solutions we barely understand. And what about privacy on a cosmic scale? If we discover a Dyson sphere, it means we've essentially peered into another civilization's realm. Is it acceptable to study them intently from afar without their consent, mining every bit of data our instruments can gather about their world? Similarly, if they have been observing us, perhaps quietly listening to our broadcasts or studying Earth with their probes, we might feel uncomfortable. Do intelligent beings have a right to examine each other secretly, or should there be an expectation of communication first? These questions have no clear answers yet, but they remind us that contact is not just a technological event, it's a relationship, one that would need boundaries and understandings. All of these uncertainties point to the need for what some call astroethics, a set of guiding principles for interactions with extraterrestrial intelligence. Perhaps the best starting point is to extend the golden rule beyond Earth. Treat any other civilization as we would wish to be treated. That means with respect, caution, and empathy. If we find evidence of their existence, we should neither panic nor behave aggressively. Instead, we should approach the situation with a spirit of peaceful curiosity and humility. Conversely, if they reach out to us, we would hope they exhibit patience and benevolence, giving us the time to understand and respond. In short, any meeting of minds across the stars ought to be founded on mutual respect and a careful regard for each other's well-being. Thinking about these scenarios in advance is not just idle speculation. It's part of preparing ourselves for a reality that could come tomorrow or decades from now. It also has a way of reflecting back on our own behavior as a species. If we must imagine presenting a united and ethical face to alien visitors, that very exercise encourages us to resolve conflicts among ourselves and behave more cooperatively here on Earth. In a sense, striving to be the kind of civilization we would want others to find might be one of the greatest benefits of the search itself. By grappling with the ethics of contact, we reaffirm values of unity, peace, and responsibility that are worth upholding, regardless of whether aliens ever answer us. For now, of course, we remain alone with our questions. No voice from the stars has spoken to us yet, and no unmistakable beacon has been found. In the absence of real contact, all we can do is continue to listen and prepare. We scan the skies and consider the possibilities, holding on to both hope and caution. And as we do, the act of listening itself has become a profound part of our story, one that defines this era of search. In the next part of our journey, we turn to that very endeavor, the patient, decades-long vigil of listening to the void, awaiting a sign that we are not alone. Night after night, year after year, radio telescopes around the world point their enormous ears to the sky, listening for a voice that may not even exist. This is the other side of the search for alien megastructures, not looking for their light, but listening for their signals. Since the middle of the 20th century, scientists have been conducting SETI, the search for extraterrestrial intelligence, by tuning in to the vast silence between the stars. They monitor cosmic radio waves and optical pulses, hoping to catch a deliberate message or even the faint murmur of alien technology at work. It is a quiet, patient vigil, one that requires faith that somewhere, someone might be transmitting. So far, the void has answered with little more than a hushed static. No confirmed extraterrestrial signal has ever been detected, despite decades of careful listening. Every once in a while, a tantalizing hint flares up, only to fade away again. The most famous of these was the WOW signal, detected one summer night in 1977. A lone radio antenna at Ohio State University picked up an intense, narrow-band radio burst from the direction of Sagittarius, a signal so remarkable that the astronomer on duty scribbled "Wow" next to the data printout. For a moment, it seemed we might have heard a whisper from an interstellar neighbor, but the signal never repeated, and exhaustive searches for it again came up empty. To this day, the WOW signal remains an intriguing mystery, perhaps a glitch, or an undiscovered natural phenomenon, or just maybe a brief hello from far away that we happen to catch by luck. Undeterred by false alarms and long odds, our efforts to listen have only intensified. Modern SETI programs are far more powerful than those of earlier generations. Projects like Breakthrough Listen, launched in the 2010s, deploy cutting-edge receivers to scan millions of frequencies across potentially billions of star systems. Where early astronomers had to tune radios by hand and check one channel at a time, Today's searches use supercomputers and machine learning algorithms to sift through torrents of data for any anomaly that might be a sign of intelligence. We're searching not just in radio, but in other mediums too. For example, scanning for brief laser flashes or optical pulses that an advanced civilization might use to communicate. We try to leave no stone unturned in this quest. Researchers have even contemplated signals via exotic messengers like neutrinos or gravitational waves, though those technologies are currently beyond us. The key point is that our ears are wider and our hearing sharper than ever before. Yet the galaxy is vast, and the challenge is often likened to searching for a needle in an ocean-sized haystack. Imagine trying to catch a faint, murmured conversation across a crowded stadium. If you're not listening at the exact right time, frequency, and direction, you might miss it entirely. It could be that someone out there is speaking, but we haven't yet pointed our instruments to the correct place or tuned to the correct channel. Or perhaps the call is so faint by the time it reaches us that it's lost under the natural background noise of the cosmos. There's also the chance that other civilizations are using communication technologies utterly different from anything we expect, or that they are deliberately keeping quiet. Given these uncertainties, it's no wonder the silence persists. Our sample of the cosmos, while growing, is still minuscule. We've only recently begun to scratch the surface of the cosmic expanse with our listening devices. This long quiet has a way of stirring mixed feelings in those who devote their lives to SETI. On one hand, each day without a signal reinforces the notion that intelligent life might be exceedingly rare. Perhaps we truly are alone, or nearly so. On the other hand, researchers remind themselves that absence of evidence is not evidence of absence. The universe is nearly 14 billion years old and immeasurably large. Waiting a few decades with a handful of instruments is hardly a thorough survey. Patience is more than a virtue here. It's a necessity. The search could take generations. Those involved in SETI often liken themselves to cathedral builders, laying foundations that may only bear fruit long after they are gone. It is a quietly heroic endeavor, working day after day for a discovery that might not happen until a far future scientist picks up where they left off. In the meantime, listening to the void has had its own profound effects on us. The very act of searching for others has brought humanity together in subtle ways. International collaborations have formed to share telescope time and data, because this quest transcends borders and politics. There is a kind of poetic unity in the image of people around the world, from different cultures and languages, all gazing up at the sky with antennas and hope, attuned to the same silence. It reminds us that we are one species, huddled around one tiny flickering star, trying to see if anyone else is out there. Even if the silence continues, that awareness of our common loneliness in the cosmos can be strangely beautiful and bonding. Of course, science demands we consider the possibility that nothing will be heard. Perhaps the great silence is telling us that advanced civilizations either destroy themselves, hide themselves, or are so far apart in space and time that two may rarely, if ever, overlap. This is one interpretation of the Fermi paradox, and it might be true. Yet, curiously, rather than leading us to despair, the silence often inspires a redoubling of curiosity. If we truly are the only ones broadcasting or listening right now, then the universe is a dramatically more mysterious stage. Why us? Why now? And what lies ahead for us in that case? The lack of answers keeps us asking questions and keeps our instruments trained on the stars. And so the listening continues. Radio observatories scan the sky through the dead of night. New space telescopes join the hunt, looking for subtle technological glints or chemical signs of life in distant atmospheres. With each improvement in our technology, we revisit the cosmic silence with fresh ears. It is often said that the universe speaks in mathematics and physics, the regular pulses of pulsars, the roar of quasars. We're listening for something different, a voice or a code that nature alone cannot produce. If one day we detect that, the silence will be broken with profound implications. But even if tomorrow's sunrise brings yet another day of cosmic quiet, we will press on. The people who dedicate themselves to this search often use words like hopeful and patient to describe their outlook. It's a hopeful patience, indeed, a willingness to wait as long as necessary, because the prize is so momentous. Imagine, one moment you are sifting through ordinary data, and the next, a line of unmistakably artificial code appears, a signal clearly crafted by intelligence. In that instant, humanity would no longer be alone. This possibility, however remote, fuels the perseverance of listening teams around the globe. It's why Frank Drake, who conducted the first modern SETI experiment in 1960, kept at it through decades of silence. It's why new generations pick up the mantle, building ever more sensitive searches. Our journey is nearing its conclusion, and throughout we've pondered what a Dyson sphere could mean, both for those who might build one and for those who might discover one. As we listen to the void, we are essentially eavesdropping on a conversation that may or may not be happening among the stars. If one day we do hear something unmistakably artificial, our view of the cosmos will change in a heartbeat. If instead we continue to hear nothing but echoes of our own transmissions, then we confront the sobering possibility that intelligent life is exceedingly rare or fleeting. In either case, a certain responsibility falls to us. Should the silence persist, perhaps we humans will have to carry the beacon of consciousness forward ourselves. Maybe we will be the ones to venture out, to construct great works like Dyson spheres around our own sun, in essence, becoming the very cosmic architects we once searched for. In doing so, we would light up the darkness for any who come after. For now, the stars above remain quiet and mysterious. The cosmic stage is still dark, but we continue to keep watch, refusing to surrender to the silence. Each day that our instruments return no signal, we resolve to listen again the next day. Because somewhere out there, perhaps very far away, another civilization might be asking the same question we are. One day, our patience may be rewarded with the faint echo of another society's existence. And if the curtain never rises on someone else's voice, then the future is ours to fill. The void may be silent now, but the cosmos remains full of possibility, and it may be our destiny to fill it with light and sound.